Assistant Professor and a Program Director of MSc Cybersecurity Program at the University College Cork, Ireland. He brings a wealth of global expertise in the field of computer science and information technology. His research interests are highly relevant to today's challenges. Prior to his role in UCC, he held significant positions at the University of Florida and Intel. Also served as a visiting scientist at the Indian Statistical Institute. On behalf of everyone, I extend a very warm welcome, sir. To you.
Yes. Okay, so before I begin, can I know like what is the time that I need to stop? Hello?
3:30, sir.
Okay, so it's 1.5 hours, right?
Yeah, sir.
Okay, good. Yeah, thanks. Okay, so can you see my screen?
Yes, sir. Yeah, it's visible, sir.
Oh, good. Okay, so to begin, so what I am going to say today is related to hardware security, okay, AI, and chip to system design. So the talk is entitled something like this: hardware security for AI in C2SD, that is the chip to system design. Okay. So before I begin, just to introduce myself, presently I am an assistant professor or lecturer in the School of Computer Science and Information Technology in University College Cork, and that is in Ireland. Okay, and over here we also have a MSc program that is in cybersecurity, where I am the program director, right? And my previous affiliations are something as this. So before joining this university in Ireland, I was a postdoctoral research associate in University of Florida in US, and prior to that, I was also a researcher in Intel. Okay, and I had joined for some time in National Institute of Technology, Jamshedpur as an assistant professor, and I was also a visiting scientist in Indian Statistical Institute, and I completed my PhD in University of Calcutta. Right, so these were like my previous affiliations. Okay. Now, regarding my present works and the present domain that I am associated with. Okay. Yeah. So essentially, along with teaching, I also do research in UCC. Okay. So the main funding that we get for our research are from two entities, that is the Research Ireland and the Horizon Europe. So like we have in India, the Department of Science and Technology, right? So in Ireland also we have something called Research Ireland, right? And this has some research centers like the Connect Center, Advanced CRT, this and that. And this center gives us some funding to do some research, and based on this funding, we try to keep some PhD and some postdoc students, right? And along with this, in UCC, we have some groups. Okay, so we have the NAS research group and the cyber security research group, right? So these are the groups that I am a part of, right? And along with Research Ireland, we also apply for funding in the EU projects. So essentially, we have the Horizon funding over here, and there are two projects that were funded by Horizon Europe to me. And okay, so these projects are not individual projects, but these projects are done based on a consortium, right? So at present, I am in the QFence project consortium and the QCloud project consortium. So this project relates to something related to post quantum cryptography and also like quantum computing, right? So these are the things. Now my research team in UCC. So essentially we all have a research group, and my research group or my research stream is entitled as Quest, right? So Quest is a short form of quantum and embedded systems technology. So as the name suggests, I do some type of research on embedded systems, hardware security, and quantum computing. Okay, so I am the faculty or the principal investigator of this group, and in this group I have one postdoc, that is Alia, and I have some PhD students also like Andrew, Shobon, Shafkat, Naim, and Sam. Okay, so this is my research team. Okay, okay. So now the talk, the present talk that I will be giving, these are divided into six parts. So definitely we will be starting with an introduction, right? Then we will be doing some like we will be seeing some fundamentals, or we will be doing a little bit of background on hardware security. Okay, then we will be moving on to smart hardware and what are the related types of attacks on the smart hardware, right? And as you can understand, the smart comes from the concept that there is some AI or ML associated with the hardware. Okay. Then the other three parts, that is the part 4, part 5, and part 6. These are essentially some of the research works that I have done previously, and these are published in some well established venues. Okay. So, these three parts we will be dealing, we will be essentially reviewing the research works that were done by me, and actually these are published, and if you want you can you can look these papers online also. So part 4 essentially deals with securing the on-chip DNN models. Part 5 deals with securing AI models in multi-tenant platforms, where we will be seeing the edge and cloud platform. Okay, and finally in part 6 we will be seeing how we can secure AI and ML workloads, right? So we will be starting with on-chip DNN models, that is single AI ML models. Then we will be moving on to some platforms, some system level platforms essentially, where these AI models can be shared by different tenants. And finally, we'll be seeing that when we have not a single tasks, but we can have like multiple tasks, and we can call them as some workloads. How to deal with the workloads, what can be the threats on the workloads, and what can be the related security mechanisms for those AIML workloads. Okay, and finally we will conclude today, right? Okay, so part one, that is the introduction. So to start with, essentially we need to understand how the industrial revolutions took place, or what were the different forms of industrial revolution, and what is the current state of industrial revolution in present time. Okay. Okay, so essentially it all started in the 1800 with the industry 1.0, or the first industrial revolution, where there was the mechanization, water and steam powers, this and that. Then it all went to industry 2.0, where the mass production took place, and even the electric power was generated, right? Then in the 2000s we saw a drift from the traditional mass production and electric power to automation. Okay, where we all focused our attention to computers, to automated electronics, this and that, right? Then in the 2010s, that is when the cyber physical systems, IoT, networking, machine learning, AI, all these things came into place, and we call this time essentially as the industry 4.0, or the fourth industrial revolution. And presently we are in the fifth industrial revolution, where we are trying to view the human robot collaboration, the cognitive systems, customization of the automated system, so that it can serve us. Essentially in industry 5.0, that is at the present time, what we are concerned with is that we are also concerned with our well-being rather than automation and the other prospects. We are essentially trying to see how these computers can serve us better, can serve us for our well-being. Okay, so if you can see in the next picture, so what is the impact of industrial revolution on society? Definitely it has developed many important things, like it has improved our health and transportation systems, right? It has also made the industrial society more organized, and definitely it has given us some value for money, right? Okay, now for the present domain, what we are interested in, we are interested in seeing the chip to system designs. Okay, so when we are considering the different IoT systems, or we are considering the cyber physical systems, essentially what you can find is that these are made up of several electronic chips. So underneath the smart home, smart city, the smart transport system, or even the retail IoT, or the smart agricultural systems, what we have inside is the chips. Okay, so now from the traditional chips that we had, we are transforming into some smart chips, And what does this essentially mean? Smart chips. It essentially means that we are incorporating AI and ML in the chip level so that it can perform better, or we can get better performance from the smart chips in our system level, right? So if you will be trying to see the cloud to thin continuum, so like there are like three stages what we can understand. That is, we can have the smart devices which are essentially the actuators and the sensors, and these are the places where the chips are means we can have a single or multi chips actuator and sensors, right? And from the smart device level, we can move into the edge level where some real time data processing can take place. And from that edge level, we can move to the cloud platform where like big data processing and storage can also be done. Okay. And in all these platforms, if you can see in the right hand side picture, okay, so we have like different hardware components. We have like the FPGAs, okay, and we have like traditional like the ASIC components also, right? And so, what does this hardware do in the edge and the cloud platforms? This gives us hardware acceleration for our systems. Okay, so with the Industry 4.5 and Industry 5.0, we are essentially moving towards the fast and flexible computing. And when we are considering fast and flexible computing, what we need to understand is that the cloud service providers must give us some type of hardware acceleration, and this hardware must be flexible enough to program. So we are essentially considering this the configurable hardware, or what we also can term as the field programmable gate arrays or the FPGAs in the cloud architectures, not only in the cloud but also in the edge platforms also. Okay, and with this, what the CSPs, that is the cloud service providers, can do is that they can provide different users to host their applications in the cloud platforms. Okay, and this is where the multi-tenant systems comes into place, right? And this is where the AI ML workloads come into place. Okay. Now, as we are considering this type of deployment of this intelligent or this smart hardware in the cloud and the edge platform, something new has come up that is called the machine learning as a service. But what is this machine learning as a service? It can be viewed that it is like an okay, so this machine learning as a service on the MLAS, okay, we can think that this is like an umbrella term. And what does this stand for? This essentially stands for a collection of various cloud-based platforms that use these machine learning tools. And what does these tools do? It essentially provides some solutions to help with the ML teams. Okay, and what are the solutions that they provide? Essentially, so they do some type of predictive analysis. They do some data pre-processing, some model training and tuning, then some run some orchestration, then also deploy some of the intelligent models that we try to develop. And it leverages the power of this cloud computing to offer to the machine learning services on the go. So if you will be seeing the stats, okay, in the right hand side, so the market growth by 2024. So see how this is being enhanced from with the help of AI. Okay, and see how this global machine learning market and these things or the artificial intelligence revenue, these things will be going up, right? Now there is a twist also. What is the twist over here? If there is an adversary in the loop, right? So what can an adversary do? It can definitely jeopardize our work. So we really need to understand what type of threats an adversary or if some users with an event mentality can present to us. And we must try to understand this type of threats, okay, and then also take some security measures to prevent this type of threats, right? So, what are the key questions that we can deal with? Firstly, what can AI and ML learn from security? The second key question is what does security learn from AI and ML? Now if we are going to combine the security and AI ML, so the third term is something like this. What does security driven AI ML look like? Sorry. Yeah. So what does security driven AI ML look like? Okay. So we will be considering this type of thing, that is the security driven AI ML, not only for on chip platforms but also for the system level. Okay. So if we are trying to view the security driven AI ML, so we need to understand how security can help AI ML and how AI can help security applications, right? So the first thing essentially is related to how security can help AI ML. So this can be like broadly classified into like three categories. That is, security can ensure the integrity of our systems that we try to develop. That is, it can produce proper results. Then it can ensure the confidentiality or the privacy of our system. That is, it can prevent the data leakage, and finally, it can prevent the misuse of AI. Okay, and how does AI help in security applications? So definitely, it learns from the different types of attacks that happens and also prevents the future attacks. Okay. Okay, so now we will be moving on to the part two, that is the hardware security. Okay, so this is our entire focus. That is, we are developing on chips, the like AI based on chip platforms, this and that. Now, if we are trying to develop this AI based system on chips or something like this, then what can be the associated security issues? Okay, so we will be discussing a little bit of background related to hardware security. So you know what is the traditional hardware design flow? That is, we have a concept or we have an idea that we need to implement. Then for that, what we need to do is that we need to give the specifications, and based on the specifications, the system designers come into place. They try to develop a design architecture, and based on that, we can have an RTL, right? And after writing the RTL codes, we need to verify the RTL, and when we are and means when we are sure enough, okay, the RTL is verified and it gives some proper synthesis, we send this to the foundries for the production, and ultimately what we get the on chips, the chips in our hand, right? So essentially, all these things was done in a single site previously. Okay, so from the writing of the RTL code to the fab stage, everything was done in a single site, but it had some problems. Okay, so the essential problem of doing all things in a single site was that we really did not have the expertise or the tools or the machinery to do everything on a single site. And secondly, we really did not have the design, like the development cost was also huge. Okay, so what people did was that they turned that into a globalization mechanism of developing the chips or the system on chips also, as you can say. Okay, and for that, what emerged was the outsourcing of the various design phases and also some integration of some third-party intellectual properties or some IPs. And this gave us several advantages. Firstly, it reduced the cost of the design. Secondly, it reduced the expertise required in a single site, and finally, it reduced the time to market. So now we can have like chips in a very small amount of time, and also the cost of the chips also came down. Okay, but there was a disadvantage also. What was the disadvantage over that? So the hardware root of trust is eliminated. So essentially, previously, what was focused was only on the software attacks, right? And the hardware was considered trusted. Okay, but when we moved on to this globalization mechanism of chip designing, now along with the software problems, we can also have the hardware problems. And what are the threats in the real SI design? So definitely we can have some threats in the design stage, we can have some threats in the fabrication stage, and even in the packaging and the distribution stages also. But we basically focus our attention in the design stage, where we can have some malicious or some untrusted IPs. That can be some soft IPs or that can be some farm IPs. Okay, and also in the fabrication stage also there can be like problems related to for like lithographics and this and that, but that is not our concern at this moment. We are only concerning or we are only focusing on the design stage. Okay. Okay, now when we are considering hardware, so what types of hardware that we are considering on? So essentially, we are considering on field programmable gate arrays and application specific integrated circuits. And as you know, these have their own merits and demerits, right? But as I have told before, also we are in industry Okay, we are also, we do a lot of work for the domain associated with industry 4.0 also. Okay, and where fast and flexible computing is required, and when this fast and flexible computing is associated, we mainly focus our attention to the FPGAs. Okay, and these FPGAs serve as very good hardware accelerators in the cloud and edge platform. So mostly my works are related to the FPGAs. Okay. Okay, so when we are considering FPGAs, so let us view some basics related to the FPGAs. That is, as we all know, that these are essentially programmable integrated circuits, and it comprises of several CLBs, that is the configurable logic blocks, and also some DSPs and some memory units, right? And computing in FPGAs, what we essentially call is that this is like a spatio-temporal type of scheduling or work that we do. That is, we compute in space as well as time, right? Now, if we have to zoom into the FPGA architecture, firstly, the most important thing that we will come across is the logic cells. These are nothing but some lookup tables that perform some arbitrary functions with some small bandwidth inputs, right? And they essentially perform some types of operations. And what type of operations that they perform? They essentially perform some operations related to arithmetic or some memory operations or some even Boolean operations. And along with the LUTs, that is the lookup tables, it also have some flip flops. And these are nothing but some registers that store some data with some clock pulse, right? Now, along with the CLBs, we also have some DSP units and some memory units. So these DSPs are utilized for multiplication and arithmetic operations, and it does some fast and efficient computing, okay, using the LUTs. And these are well utilized for the neural nets, DSPs, okay, for the neural nets, and also for some operations related to image processing also. And finally, we have the memory units. And the memory units over here are essentially the VRAMs, that is the block RAMs that we have. And for that, we have like several fast memories like the RAMs and the ROMs. Okay, so, so this is the thing. Now, when we are considering about hardware threats, so the first thing that comes to our mind is the hardware trojans. Okay, so we have a lot of like trojans in software also, but how this hardware trojans are essentially different from software trojans. So these hardware trojans are nothing but some malicious intentional modification of the circuit design. That is, we put some additional logic gates over there, which essentially remains dormant during the testing and the initial phases of operation, but eventually gets activated at runtime via some internal or external trigger. Okay, and this mechanism of remaining dormant during the testing and the initial phases of operation and getting suddenly activated at runtime came from the like the historic war of Troy, okay, where the Greek soldiers entered Troy within a wooden horse and remained there silently until a trigger came place, from after which they came out from the wooden horse and opened the gates of Troy, after which the Greek soldiers entered the city of Troy and even plundered it, right? So, based on this story of the history battle of Troy, right, the concept of hardware trojans was also generated. Okay, not only hardware trojans, but anything that is related to trojans, that is software trojans. Okay, so after it gets activated at runtime, what the hardware trojans does is that it tries to jeopardize our the security of our system. And what type of security elements does this hamper? Firstly, it can attack our integrity of the system. Secondly, the confidentiality of the system. Thirdly, the availability of our system. That is, it essentially attacks the CIA triad, right? Okay. And along with the hardware trojans, another thing that is quite important is IC counterfeiting, or simply the issues with the fake IPs or the fake ICs. And what are these fake IPs, or what are the counterfeits that we understand? These are something that really do not meet their specification, or even in simpler terms, it does not perform as per their required standard. Okay, so these are like overproduced items or out of the specs items or some defective parts or some like the cloned ICs or some recycled ICs, this and that. Okay. So how all this counterfeits comes into place? Mostly This takes place in the recycling process. Like whenever we do not use an like whenever our any of our electronic devices malfunctioning, we essentially throw it off and it goes to a recycling center. Now we need to understand that when we throw away our electronic components, so definitely all the electronic chips does not malfunction. Maybe only a single or one or two chips malfunctions that they usually like jeopardizes the entire system functionality. Now, from these electronic systems or from the PCBs of these electronic systems, the ICs are taken off and then the ICs are recycled and even these are refined and remarked this and that, and then they are ultimately sold as new. And when these counterfeit components are used in some critical applications, then what can happen? Then the critical applications can be jeopardized. Okay, so in a much shorter time, the critical application will fail, which we haven't realized, and this is what relates to some type of like some okay, like some malfunction in some critical application, and this can result in some fatal incidents. Okay, so this is the thing. Now this is a picture of what can be the vulnerabilities in the e-supply chain. So if you see that from the design stage to the fabrication, assembly, distribution, lifetime, and the recycling. So definitely in each and every stage there can be associated with different types of uh, vulnerabilities. But as we told, our focus is essentially in the design stage where vulnerabilities are related to IP piracy, untrusted IP vendors, CAC tools which are used for the design and also for the system integration. Right. Okay. Now we move on to smart hardware and some related attacks over here. Okay. Now when we are considering the smart hardware, what we essentially mean, what we try to mean by smart hardware, and what can be the possible threats on the smart hardware, what can be the possible attacks on the smart hardware. This is what we need to know before we move on to the solutions. Okay, so, firstly, what is smart hardware and what is the need of the smart hardware, right? So, as you understand that presently we are in industry 5.0 and we do a lot of work related to cyber physical systems, IoTs, which are essentially in the domain of industry 4.0. Okay, and all these applications we try to integrate AI and ML in our applications, right? So what we need to do is that not only in the system level or in the software level where we are trying to incorporate AI ML, what we also need to do is that incorporate AI ML in the chip level. So when we try to incorporate this AI and ML on our system on chips, what we essentially get is the smart hardware, that is AI integrated chips. Okay, so by smart hardware, what we essentially mean is that AI deployed on system on chips, right? So present day user applications are smart and intelligent, which are associated with complex neural networks and even smart AI algorithms. And hence, with the combining this AI ML with the chip development, what we get is the AI chips, right? And this we call the smart hardware. And these are very much essential in any type of applications that we are trying to develop. But what about security? So security is also important, right? So if we just focus on the design, then the design can be hacked by any type of adversary, or the different adversaries can put down different attacks on the system. Therefore, we must make the system secure as well, right? So we must consider the security. Now, what is the smart hardware and how we try to develop it? Essentially, we try with some smart applications. We have some smart applications in our mind. For that, we try to do a neural architecture search, that is the NAS, and we try to select a neural architecture model that is well aligned with the smart applications, and based on okay, then we try to make that model perfect enough. And how we try to do it? We try to train the model. We try to we try with different data sets this training and learning of the model. Okay, and then uh, and then try to see whether the results given by our model by the model that we are trying to develop is uh, as per our requirement, right? If we can do this, this is quite fine. Or else we move back to the training and the learning stage where the neural network waves are essentially modify until and unless we are satisfied with the results, right? So if we will like after we get a neural network that gives like proper results, what we try to do is that we try to transform it into the hardware model. Okay, and for the in the hardware model, definitely we have some gates level diagrams, this and that, and their weights are also stored in the memory in the memories, right? We essentially implement the model in hardware. And how we implement the model in hardware, definitely we have a lot of tools for that. And like the most important tool that is available is the HLS for ML. Okay, so these are well available tools. If you can if you wish, you can just go and try to see how these things works, right? Now the thing is that when we develop all these AI chips, this and that, right? So we put down a significant amount of time, we put down a significant amount of money and effort for generating this type of models, and all these things relates from the data set collection, then the training mechanism, then the learning mechanism, this and that. Okay, so we are putting in a lot of effort, money, time, this and that, and therefore these can be considered as the intellectual properties, which are definitely confidential and definitely costly. So definitely, like an IP that is developed by IBM, IBM will never like this IP to be stolen by Intel. Okay, so this should be well confidential, and along with confidentiality, there comes a thing of cost. Okay, so like if the chip, if an AI integrated SoC that IBM has developed for this purpose yeah, is stolen by some rival company, then what can happen is that along with its work, it will lose a lot of money or its budget. Okay, so, what is the goals of the adversary? Definitely, as I told, the adversary will try to attack the CIA client. And what is the CIA client? That is the confidentiality, integrity, and availability of the system will be jeopardized or destroyed. Okay. So, what can happen when an adversary will attack the system confidentiality? So, when an adversary attacks the system confidentiality, then the adversary will try to steal the model, that is, it tries to steal the weights and biases of the system, and then perform a reverse engineering to essentially recreate the model. Okay. Secondly, it can attack the system integrity, and if it attacks the system integrity, what does this mean? That it tries to make the system provide wrong results or some erroneous results. That is, it will cause the model to malfunction, right? And finally, system availability, that is, it will try to do some denial of service, or for real-time systems, it will make the systems miss their deadlines, or by creating some finite or some infinite delays. Okay, so these are the essential threats that can be associated. Okay, okay, now having done these things, so as I told, the last three parts of this talk will be basically based on some of the previous works of mine. Okay, so the part four is related to securing on-chip DNN model. So definitely, I have done some works related to this, and where I have tried to show that how this LSTM on chip can be secured, and also CNN on chip can be secured. So the LSTM related security on chip was done with my was done with a group in University of Florida and University of Illinois Chicago, right? And that was published in IJCN. Okay, so but that I haven't focused in this talk due to the time limitations. What I have focused in this talk is another of this DNN model, that is the convolutional neural network. So this work that I will be discussing over here is essentially uh, published in IEEE ISB in 2024, right? So it essentially deals with the secure, energy efficient implementation of CNN on FPGAs, okay, for accuracy dependent real time task processing, right? So what we have done over here is that we have tried to see what some smart intelligent solutions in real time application specific neural networks, okay, which are essentially created for embedded systems. Okay, Now the bottleneck when we are trying to develop this system, that is the CNN model, and implement it on some FPGAs or some system like some reconfigurable hardware, this and that. The bottleneck is that it requires a huge amount of resource, and it also relates to a lot of power consumption also. Okay, for implementing such neural networks, right? Now the CNN implementation on FPGAs is associated with with a lot of power and a lot of resource utilization. So these are well suited for cloud environments, right? But if we are to consider this for the device level, that is in the actuators and the sensors or some handheld devices which are like resource constant and low budget, okay, then how we can develop that? And along with the design, we also need to keep a mind that this should be secure enough, right? So definitely there have been some previous works related to the design, but not related to security. Definitely on how to develop some CNN designs that will be of like low latency, low power, low resource consuming, and what they have used over there is that they have used the pruning technology, right? So they have tried to cut the CNN model, remove some parts, okay, and then fit it on the embedded system. Now, what those creates is that those reduces the accuracy of the system, and definitely these are not suitable for some accuracy dependent hard real time systems, because for hard real time systems along with the deadline we really need some like accurate results. Okay, now what our work focus on is that we essentially looked at some pre-runtime like lookup memory access, okay, for this CNN implementation on FPGAs, and then we tried to reduce the resource utilization, latency, and power based on the memory spaces which are available, right? The via this mechanism, what we achieved was that we achieved the high accuracy without the pruning, right? And so this was quite suitable for like accuracy dependent real time systems. And we also analyzed the variation of throughput and power with respect to the availability of the embedded memory blocks, okay, for Linear 5 CNN model. So the background is something like this. So essentially, CNNs are used for a wide range of applications like image classification, computer vision, this and that. And this CNN has a lot of layers also, okay, like the convolutional layer, polling layer, activation layer, okay. Now the structure, weights, and biases vary based on the targeted application. So we consider okay, definitely there are a lot of CNN models, but for our work we consider the linear file architecture, right? So if you see how the CNN Linux 5 model was implemented in the FPGA in this diagram. So corresponding implementation, okay, we utilize a zinc board. Okay, so the PS, so as you know, the FPGA comprises of a PS and a PL platform. So the PS comprised of the quad core ARM Cortex A53, and which was connected to the 16-bit DDR RAM, and which can also access the PL, and the PL was associated with a controller that was responsible for controlling the various flows of the CNN models, okay, like convolution, polling, this and that. So the related works of the CNN implementation, if we try to think, okay, so there were some optimization models that were associated with some group unloading strategy, then some data sharing, then some parallelization thing, right? And there were some security strategies. Okay, these security strategies never focus on the optimization techniques, and optimization strategies never focus on the security techniques. And the security based models, what they try to do was that they try to first get the base hardware, they try to insert some noise, then they try to shuffle the memory reads and writes, and also use some genetic algorithm to mitigate the timing difference. Now the thing was that the security driven AI modeling was not done previously. So this is what we have done in our present work. Okay, so if you try to see the comparison table, so you will see that there are the optimization based models, there are the security based models, but the optimization based models and the security based models never complement each other. And Okay, so they never focus on the security driven AI strategy of security driven AI design strategy, and this is what we propose. Okay, and what are the threat models that we consider over here is that we consider that the the confidentiality aspect. Okay, so what happened was that well, actually what happens is that the adversary tries to steal the weights of the system. Okay, they try to steal the weights of the neural network, and then they try to reverse engineer. Right, now if we can prevent the stealing of the weights and biases, if we can do that, then so definitely the system confidentiality will be maintained. Okay, and another thing that we focus, as we told, that was accuracy. Right. Okay, so see, we have defined it into three parts. That is the leakage of the confidential information. That is what we discussed. That is to prevent the adversary stealing the weights and biases of the system. Then how to reduce the resource power and also maintain the accuracy of the system, and also the issue of timing. Okay, how we can reduce the timing on the latency of the system. Okay. So what was our proposed mechanism? What we try to do over here is that we try to see what are the unutilized memory or the embedded memory blocks that are unutilized in the normal design of the system. Then if we can find what are the embedded memory blocks or the embedded memory blocks that are not utilized or the unutilized memory spaces, then what we can do was that we can pre-compute some of the complex operations and store the results over there, and then fetch the data, okay, at runtime. So this was all our key concept. Okay, and how do we did it? We had five design steps. The first design step was to develop a system architecture that can support our notion, and for that what we tried to do was that we tried to develop the system um, as some logic computation and some memory block accesses. Okay, so these are repeated, right? So this memory block accesses had a set of memory blocks arranged in a matrix format. So these were like the embedded memory blocks. You can view as essentially you can imagine the unutilized embedded memory blocks of the system, and over there we try to uh, deploy some pre-computed functions. Okay, so these are very complex and it takes a lot of time and resources, and even consumes a lot of power to be done at runtime. What we try to do is that we try to uh, do all these things in the offline phase and deploy them, and when they are needed they are essentially fetched from the memories, right? So if we have to do this, what we need to do is that we need to develop our data flow graph, right? So we are now going deep into our model and how we have designed it. So essentially, for the function, for the resource consuming and the time consuming function, we essentially develop a data flow graph, right? And in this data flow graph, we try to analyze the different types of nodes over there, and then how we can fuse these nodes. And after fusing these nodes, we try to order the nodes in the order that is which is the most time consuming, power consuming, and which is the least time consuming and power consuming, and then we map them to the available memory blocks. Okay, so this is essentially the block diagram of our workflow, where we have the EMB organization on and the design organization, and after doing that we have the mapping of the different functions to the different memory blocks, right? Now, how this mechanism can essentially mitigate the other problems? Okay, so essentially this can prevent the leakage of confidential information like the weights and bias, because over here we do not store the weights and biases in the memory. What we store is we store the pre-computed results. So definitely, if an adversary have to steal the information, they cannot steal individual weights and biases. They can steal as a total means the pre-computed results, and if they steal the pre-computed results, ultimately they cannot do any reverse engineering. Okay, so this is how we can ensure the confidentiality of our system, right? And also we reduce the resource power resource and the power utilization. Why? The reason is that we are not doing total functional. We are not computing total function at runtime. What we have already done that in the in the offline stage, and we have just stored the results over there, right? So we just need to do a fetch operation, and this fetch operation does not take a lot of resource and the power. Okay, so essentially we are also reducing the resource and the power, and also we are ensuring the accuracy. Why we are ensuring the accuracy? Because we are not doing any type of pruning or optimization, right? We are doing pre-computation and storing that in memory blocks, right? Then comes the issue of timing. Okay, so what we do over here is that we do not do the total computation, but we just do a fetch and fetch and implement type of thing. And this fetching and implementing does not take a lot of time. So ultimately, we gain a lot of latency. Okay, okay, so experimentation and results, as you can see over here, that we have implemented the Linux 5 CNN model. Okay, we have written some Verilog codes and implement that in the Xilinx Vivado platform, which are targeted to the Zinc board, right? And after this, we try to determine the free EMBs and then view it in a matrix format. Okay, and these are our results, and these are also like compared with some existing works, right? So you can see that our work better, far better in terms of power, throughput, energy efficiency, this and that. Okay, so there are some graphs, right, related to throughput analysis. So you can see over here that the throughput increases a lot, because like when we are taking less time, so definitely we can process more number of tasks within a time span, right? Therefore, the throughput increases. Okay, and also the power decreases, so because the fetch and implement type of operation with the available memory blocks. Okay, so this takes very less amount of power, rather than in comparison to the power consumed by for executing like complex functionalities, right? So the power consumption reduces a lot, and also, as we discussed, the security. So the memory look up this type of things. So for this type of things, the time, okay, the access time is almost the same regardless of the operations. But if the operations were different, then the memory access times will also be different, based on which the adversaries can reverse engineer. But over here we are like we are maintaining the same memory access time, and therefore we are essentially maintaining the confidentiality of the system. Okay. So the next thing, that is the part five, is related to securing AI models in multi-tenant platforms. So now from the chip level, we are trying to move into more of a system level. Okay. So over here, we will be essentially considering some edge and cloud platforms. Okay. So this work was done with one of my friends who was in Intel at that time. Okay, so you can say that this work was with a collaboration with Intel, but presently he is in Broadcom, right? But when this work was done in 2023, he was in Intel. Okay, so this work is entitled as a self-aware security approach for real-time neural network applications from row hammer attacks in multi-FPGA, multi-user environment, and this is published in the IEEE DFT 2023, which was held in France. Okay, so what we essentially do over here is that we consider a system where we have a number of FPGAs and a number of CPUs, and this system is accessed by a number of users, right? So essentially, we consider a cloud environment that hosts like multiple users, and each FPGA, the cloud environment that hosts a number of FPGAs basically, and these FPGAs essentially caters to a number of users, and these FPGAs have a number of virtual portions. So essentially, we are now considering an FPGA which is partitioned, okay, into number of virtual portions, right? Now, what can happen over here is that we can have a number of task schedules, and these schedules are essentially spatio-temporal schedules. That is the scheduling is done over here with respect to space as well as with respect to time. Okay, so a schedule over here, when we try to execute a schedule, so definitely we need to change the tasks over here. And for that, what we need is that we need to have the bit streams, or we can call these bit streams as reconfigurable intellectual properties, or the RIPs. Okay. Okay, so these RIPs, or these bit streams, are essentially of the programs or the functionalities that we need to execute, and these functionalities are are associated with the smart applications which are stored in the repository or the resource pool. Okay. Okay. So what is the thread model over here? The thread model is related to users who basically accesses neighboring portions of the memory, right? So when we essentially partition the FPGA into a number of virtual portions, we also essentially partition the memory into some memory portions. Okay, so you can think that different users are essentially associated with different FPGA VPs, and they also are associated with different portions of the memory or the local DRAMs, right? Now, uh, by this, what we mean is that the memory is essentially shared by many users. Okay. Now, what can happen over here is that a malicious user can cause some row hammer attack. And what is that row hammer attack? It essentially means that a malicious user can will try to access its rows yeah, at such a high frequency and power that it will cause some bit flips in the neighboring nodes. Now, see in the diagram, if user 1 is malicious, okay, and it accesses this row 3 in some high frequency and some high power, then it will cause some bit flips in row 4 that is associated with user 2. And if this bit flip values are used for computation for the user 2, then definitely the erroneous results will be generated, right? So user 1 is doing nothing illegal over here. User 1 is doing something legally, but the effect of this is happening to user 2. Now user 2 may be associated with some critical operation, right? And if due to the effects of user 1, user 2's computation is jeopardized, then definitely this will not be a good thing. Okay, so we need to have some protective mechanisms over here. So what was our proposed solution? The proposed solution was that we try to develop some hardware agents over here, right? So this hardware agents essentially works based on the observe decide act, that is the ODA paradigm. Okay, so we essentially deploy a hardware agent for each of the FPGA platforms, and these agents can like communicate among themselves based via some shared memory blocks, right? So see over here the detailed thing. So if you see the diagrams over here, right? So there are some of the FPGAs over here, and these FPGAs are associated with some hardware agents. Okay, these hardware agents can communicate via some shared memories, and definitely there is a bitstream repository where the reconfigurable intellectual properties or the RIPs, or you can say the bitstreams, are held. Okay, so what happens over here is that there is a set of schedules or the spatiotemporal schedules for each of the FPGAs. Now the hardware agents tries to view whether there is some anomalous function going on in some FPGA or not. If some anomalous function is going on, then it will outsource that the task to some other hardware agent to be executed in some other hardware platform. But for that, we really need to understand if there is some vulnerability or not, and how we can understand whether there is a vulnerability or not. Definitely, we will be needing some parameters to understand. So the parameter which is required for observing or monitoring is the memory access per unit time or the MAPUT, or we can have some memory data that based on which we can do some comparison. Okay. Now, if the values of the parameters mismatch, then definitely some anomaly is there. Okay, so a flag is set up for some corrective action. And regarding that, what the agents does is that they try to perform some action or they act. And how they act, they essentially outsources the task to some other platforms to be executed until the mm, until this the problem is resolved. Okay, and to communicate with the other agents, they essentially do that via uh, some uh, some shared memories, right? Now, if you try to see the experimental results, as usual, we have written a Verilog course, but okay. But over here, these Verilog course are targeted towards the ARIA 10 FPGAs, Intel ARIA 10 FPGAs, right? Now, for generating the row hammer attacks, what we try to do is that we try to develop some programs that are associated with some very high frequency operations, right? So when we consider to analyze our results, we really need to take some parameters. That is the success rate parameter. We can also call this as a task success rate. Okay, and this task success rate is defined as the number of applications that are completed without fault to the total number of applications that are scheduled. It is essentially a percentage ratio. Okay, and also we really need to find out what is the overhead of our security elements, right? So the resources used by the security components to the entire system resources when viewed as a percentage ratio, this is essentially our overhead over here. Okay. So if you see what is the task success rate to the number of FPGAs or the different number of frequencies, you can see over here, and also you can also see the task success rate with respect to the increase in the number of faults. So if you see the task success rate increases with the number of FPGAs and the task success rate decreases okay, with the increase in the number of faults, right? Okay, now some overhead analysis with respect to the number of FPGAs. Okay, so if you see over here, the overhead reduces with the number of FPGAs, and and if we consider the workload, okay, which we essentially normalize it. So essentially, the overhead is definitely more when comparing with the Mahmoud strategy. Okay, but overall, what happens is the area overhead increases linearly with the increase in the workload. Okay, as more records needs to be kept in the agents or the hardware agents. Okay, okay. So I still have some time to discuss the last work. Yeah. So the last work is essentially associated with securing AI ML workloads. So now as we have moved on from the chip level to the system or the edge and the cloud platforms. Now, as I have told over here, we have like multiple tenants over here, and now we also have not only a single AI or ML task, but we can have like a number of AI ML tasks. Okay, so we essentially now we are dealing with the AI ML workloads, right? And this portion of the talk is essentially based on the work that is published in IEEE ISVLSI 2025 that was held in Greece. Okay, so this work was entitled as TS, that is the time aware split computing to secure AI ML workloads for FPGA based edge platforms against some unintentional delay. So as you can understand over here, timing is considered over here, and when we are considering timing, definitely it is related to some real time task operations. Okay, and along with this, another thing that we are considering over here is the split computing, right? Now we are trying to do some split computing to secure our AI ML workloads. Okay, and definitely the target platform is the FPGA based edge platforms now. Okay, so now see over here the a brief introduction. Okay, so you already know about the ADAS systems. So the ADAS systems essentially deals with the advanced driver assistance systems, right? So the present era is definitely witnessing a heavy deployment of this artificial intelligence and the machine learning based functionalities in this automobiles, avionics, this and that platforms, right? So what happens over here is that we have these edge platforms and we have the hardware accelerators or the FPGAs, and this does not serve or this does not only work for a particular operation but for multiple operations, right? So we have this AIML workloads over here. Now the vulnerability of hardware like the hardware trojans may cause this unintentional delays over here. As I told that over here timing is quite important because you know these are like real time systems, and if some unintentional delays occurs then definitely this will jeopardize the entire schedules. Okay, and ultimately if this delays takes place then what will happen, it will cause malfunction to the systems, right? So in the present work, what we are trying to show is that we are trying to propose a time-aware split computing approach that can essentially secure the AI/ML workloads for the FPGA-based edge platforms. Okay, against the unintentional delays that essentially jeopardizes the system availability. Right. Okay. So, what were the key contributions of this work? So, essentially, the key contributions are stated as follows. So, we try to develop a strategy for split computing that is targeted towards multi FPGA based edge platforms via analyzing with the DFG. So, DFGs also we discussed in one of our previous works. So, we also focus on the DFGs over here because if we need to do some analysis, we need to have some type of visualization effect, right? And DFGs gives us a perfect visualization effect for the RTL codes that we write. Okay, then we try to formulate a hybrid offline online strategy for security driven timing aware split computing, right, against some unintentional delays due to the vulnerability of hardware. Okay, then we develop some low overhead time splitting agents that ensures the security at runtime by performing dynamic time aware split computing. Okay. And finally we enhance the task success rate. Okay. For some edge platforms that are associated with mission critical AI/ML workloads. So essentially, there are four contributions that is related to split computing, developing a hybrid offline-online strategy, then developing low overhead time aware splitting agents, and finally enhancing the task success rate. Okay. So the background over here, okay, so we have tried to categorize the background into three parts, right? The first part is associated with executing some real-time tasks on FPGAs like focusing on the CNN model on FPGA, LSTM model on FPGA, but all this was does not consider a set of AI/ML workload. They consider only single task, but not a workload. Secondly, the speed computing for AI/ML workloads. Okay, so this have been focused previously. So yeah, the speed computing for AI/ML approaches have definitely some authors have definitely focused previously. You can see in the citations. Okay, so the authors over there essentially consider the splitting the AI/ML models into layer wise to execute them on the FPGAs, but they do not consider the speed computing for generating the task schedules or more specifically the real time task schedules, and also does not focus on ensuring security. So the security driven scheduling have been focused by us previously for the cloud and the edge platforms against different types of hardware attacks, and we also try to develop some low overhead agents to ensure the security. However, these works do not focus on the split computing category. So in this work, we essentially bring into focus the split computing approach for the hardware schedules, right? Now the system model. For the system model, definitely we consider not only one FPGA but multiple FPGAs. We consider an edge platform that is associated with multiple FPGAs, right? And we try to execute a series of works over here. That is, we consider a task schedule or a workload over here, right? So the FPGAs must be configured with different bit streams or reconfigurable intellectual properties to execute different types of tasks at different amounts of times, right? That is to execute a schedule. And these RIPs are essentially procured from different vendors or stored in a resource pool or a repository. And in this work, we do not consider partitioning the FPGA, and we also only consider an FPGA executes one function at a time, right? Uh, okay, but in the journal version that we are planning, we are going to consider the that is that the FPGA is again divided into multiple portions with executing multiple tasks on these different virtual portions, right? However, the FPGA fabric can be definitely reconfigured into different. It can be definitely configured at by the different bit streams on the IIPs or the RIPs at different instances. Okay, so over here what we have, we can have a sample example or an illustrative example that you call that. Over here we have this uh, number of subtasks over here. So alpha represents the arrival time of the subtask, row represents the reconfiguration time of the related bitstream on the RIP on the FPGA, epsilon represents the execution time, delta represents the deadline of the task, and chi represents whether the task is mandatory or optional. Because when we are considering this AIML like the tasks, okay, so if you try to view the AIML task, so this task can be associated with one or more intelligent functionality. Okay, so this can be so this can have like different portions which we can view, which you can say that okay, these are of different criticalities. Some parts are like mandatory. Okay, so we really need to execute them, and some part are like optional, right? So these mandatory subtasks we denote as M, and the optional subtasks we denote as O. Okay, so the mandatory subtasks are essentially those portions of the functions that are very important for result generation, and the optional subtasks are some that are associated with the quality of result generation, like the refinement or the loops. Okay, so this gives us better quality of results, but these are optional, but still we can have the output, right, without having the optional subtasks. So the threat model over here is that we can have like as we already discussed, that is we are dealing with the availability, system availability in consideration, and for that we can have the finite and the infinite delay. So what the hardware trojan does is that the hardware trojans can cause some finite and the infinite delays over here. Okay, so these hardware trojans can be present in two places. One can be present in the bit streams or in the reconfigurable intellectual properties that are essentially procured from different third-party vendors and stored in the repository. And secondly, the hardware trojans can be present in the FPGA fabrics. Okay, so we really need to handle these two types of systems. Okay, and these essentially jeopardize the schedule or the system availability is at stake. Okay, so the proposed security mechanism is something like this. This is essentially a hybrid offline online strategy. In the offline stage, what we do is that we try to analyze the functionalities based on some DFG, that is the data flow graph, and based on this analysis, we try to determine some of the split points in the model, and based on that we try to develop the schedules. And in the online stage, which is mostly done by the hardware agents, right, we try to do some monitoring, some fault diagnosis, and then handle subtasks during the anomalies, right. So in the offline stages, as you know, the first stage is associated with examining the workloads with some data flow graphs. Okay, the second stage is determining the split points. That is how we can find some essential split points within the task and also within some subtasks also. Okay. Then we try to develop the schedules based on the split points. And in the online stage, as we told, that we try to develop some hardware agents, and these hardware agents are called TS, that is the time aware schedulers. Okay, so these low overhead hardware modules are associated with this FPGA platforms. They can communicate again among themselves via some shared memories, and when they detect any abnormalities, they just outsource their tasks or offload their tasks, right? So the first stage is definitely monitoring, and this try to monitor the present workings based on the time. Then if it finds that there is a mismatch in the timing, then it raises some flag. That is, it tries to like trigger the fault diagnosis. And for fault diagnosis, what it does is that it tries to execute the same task, but with a bitstream or with a reconfigurable intellectual property, that is the RIP, that is procured from some other different vendor. Okay, now if the same fault persists with the other different vendor also, then definitely this is associated with the FPGA platform, that is the hardware trojan is present in the FPGA fabric. But if the other fabric does not give that result, what we consider is that the bitstream is anomalous. So the third party vendor who essentially supply that bitstream needs to be blacklisted, right? So now, okay, during fault diagnosis, we need to handle the subtasks also, right? To handle the subtasks, so definitely what the agents will do is that they will communicate with other agents and try to see if those can be outsourced. Okay, but the subtask can be again a mandatory subtask or an optional subtask. Now, if the subtask is optional, so definitely we do not need to outsource it, and that can be printed, right? Now, if the task is mandatory, then what will happen is that the other agents will try to see whether this mandatory subtask can be fit in their FPGA schedules, right? If there is some vacant space or something, it will fit over there. If there is no vacant space, then what it will try to do is that it will try to decrease the execution time by enhancing the dynamic clock management unit, that is the DCM. That is, it increases the frequency of operation. Okay, and but still, if it cannot, then what it will do is that it will try to print some of its optional subtasks, okay, and fit it over there, right? So this is how it tries to do. Okay, so for experimentation, what we do is that we try to develop the MLS bench. Okay, so we essentially consider the MLS bench, uh, this the set of tasks that is given in this benchmark set. Okay, that comprises of more than 6,000 tasks, and we consider the Verilog designs of this subtasks in the benchmark tasks in this benchmark. Okay, so we develop this, and we target a multi FPGA platform that is related to Vertex 5, Zinc, and Spartan 6. Okay, and for generating the thread, we also consider some hardware Trojan horses from the trust sub, right? And that causes some unintentional delays at runtime. For generating finite delays, we consider the buffers, and for generating the infinite delays, we consider some loops over here. So to analyze the results, we consider the task success rate. So as you can see in the graph, the task success rate versus the percentage of optional subtasks. So see over here, the task success rate essentially increases. Okay, with the increase in the number of the optional subtasks, because when the number of optional subtasks increases, we have a lot of space to print, okay, the optional subtasks and execute the mandatory subtasks, right? So essentially the task success rate increases with the increase in the number of optional subtasks. Then we do some analysis with the task success rate with some task deadlines, basically. Okay, so uh, so essentially, when the task deadline is more, right? So the task success rate will increase. Because when the task deadline is more, then we have the flexibility to increase the frequency of operation and execute the task in a lower amount of time. Okay, so with the increase in the task deadline, so definitely the task success rate increases, right? Then we do some resource utilization analysis on the security elements. So we try to increase the number of FPGAs, and we try to determine what are the LUTs, flip flops, slides, DSP blocks, and the VRAMs that are utilized over here. Okay, so we definitely see there is an increase in the number of resources with the number of the FPGAs. Why? The reason is that when the hardware agents needs to handle more number of FPGAs, then it will need to have more like a table relating to the other hardware agents, because with the number of increase in the number of FPGAs, the increase in the hardware agents is also there, right? So it needs to have like an increased length of a table where it can maintain the records, essentially. Okay. Okay. So now I think I am on time. Yeah. So what we'll do is that we'll try to okay, I'll do a quick conclusion, and if you have some questions, you are free to ask me some questions. So to conclude, what I can say is that in the present era, we are witnessing the deployment of smart hardware in the cloud to thing optimum, and this also serves a number of tenants or a number of users at the same time. Okay, and when this is there, so different security issues also arise, and we are mostly associated with developing uh, secure design framework, okay, where we can have like security driven AI and ML for the like the cloud to thing content. Okay, so from the cloud to thing continuum. Okay, so this is what I have to present today. Okay, so before I end, what I will be saying is that, so you know this ISBLSI conference, so this conference is held around the globe. Okay, so this time this will be held in India, in Kolkata. Okay, so definitely I believe there will be some support for the Indian authors, right? And I am the publicity co-chair of over there. So I request you all to submit some papers in ISBLSI 2026. Okay, so this time this is being held in India. Okay, but yeah, in the next time maybe it will be going to US and then again Europe and then again Asia, right? But when it is held in a global platform, I don't think that they give some support to the Indian authors. But as this time this will be held in India, so definitely they will be giving some support to the Indian authors. Okay, so this is the thing, and I will be ending over here. So thank you. And if you have any questions, please feel free and ask. Right?
So, any questions from the participants? Sir, it seems there is no questions.
Yeah, it's fine. So like if they will have any questions, so they are free to email me. Okay, so it will be good. Thanks on.
Thank you, sir, for the wonderful session. Your deep knowledge and clarity of the explanation add an immense value to this program. I extend our sincere, heartfelt gratitude for the variable presence and the insightful address. Thank you, sir.
Thanks. Okay. Bye.
Dear participants, please wait for 5 minutes. The resource person will join.
ഞാനൊരു 10 എടുത്ത് ഇതേപോലെ ആക്കി വെച്ചിട്ടുണ്ട് നമ്മുടെ കടായി ചൂടായ ശേഷം അല്പം വെളിച്ചെണ്ണ ഒഴിച്ചിരിക്കുക ചൂടായ വെളിച്ചെണ്ണയ്ക്കകത്തിട്ട്
Yes. Hello.
Harish, sir, am I
Hello.
able to?
Yes, yes. Am I audible?
Yes, sir.
Okay. Okay.
It's my pleasure to welcome Dr. Harish V, a postdoctoral researcher and a fellow from the prestigious Trinity College, Dublin, Ireland. Dr. Harish brings over a decade of invaluable experience in the specialized field of VLSI and digital design verification. We eagerly anticipate the expert insight he will share for enhancing our academic and technical knowledge. On behalf of everyone, I extend a very warm welcome, sir. Over to you.
Thank you. So let me share my screen. Okay, may I know whether my slide is visible to all?
Yes, sir, it is visible.
Okay, thank you. So thanks for my introduction and thanks for the opportunity. So can we start?
Yes, sir, yes.
Okay. So good morning. Sorry, good evening, everyone. So today we will be discussing some basics of functional verification. That is, what is the significance of functional verification in front-end VLSI design, and how what is the impact of AI in functional verification. So this is a famous quote from by Bergeron in the book Writing Test Benches Using System Verilog. Verification is not a test bench, nor is it is a series of test benches. Verification is a process used to demonstrate that the intent of a design is preserved in implementation. So have you heard about the FDIF bug? Anyone heard about FDIF bug? There was a bug which is reported in 1994 in Intel process.
car stereo.
So the Pentium FDIF bug was a hardware bug that affected floating point FPU at early Pentium process. Because of the bug, the processor would return incorrect binary floating point results. So that shows the significance of verification. Even a small error done by verification engineer can cause big loss to company, also to the product. So that was reported by Thomas R. Nicely, a professor of mathematics at Lindbergh College. So that cost around $465 million against the earnings of Intel. So this is the sum of the recent study done by Siemens. So this slide shows the significance of verification engineers in industry. So the first graph shows the mean peak power of engineers in RC Core IC project versus number of years. We can see that from 2007 to 2020, the complexity of SoC design increases. So the peak number of verification engineers to the design engineers increases. We can see that in 2020, the number of peak engineers in verification is 11.4 compared to 10.3 for design engineers. The second image shows the percentage of RC or IC project time spent in verification.
Signature.
We can see that in 2020, the x-axis shows the percentage of RC or IC project time spent in verification, and y-axis shows the percentage of design projects. We can see that in recent, around more than 80% of verification engineers are spending more than 25% of design projects. So this is another study done by design verification Siemens. So we can see that this is a percentage of doing verification and percentage doing design. So we can see that the number of verification engineers are comparable to the number of design engineers. And this is the verification cycle. These are the test planning, test bench development, creating test and running simulation, debug and others. We can see that around 41% of time the verification engineers are spending debug, and 25% time the verification engineers are spent on creating and test running simulation.
ultra
So this whole slide shows the significance of verification in industry or in current design cycle. We know that the complexity of design and the test patterns are increasing nowadays. So verification become a very complex task today. So can we move forward?
avastha
Is everyone is following?
Yes, sir.
Okay. So this is the plan for today's section. Initially, I will go to the introduction to verification, and if we want to discuss AI for verification, the important concept is coverage in system Verilog and UVM. So we'll discuss coverage in system Verilog and UVM, constraints, assertions, and coverage, and we'll discuss some open source tools for verification, and we'll also discuss some results in verification.
ഞാൻ ചോദിച്ചു കണ്ടിട്ട് നീ ആ മെഷീൻ നേരിട്ട് വെച്ചിട്ട് കാര്യം ചോദിക്കാനായിരുന്നു.
So can I know all of you are familiar with system Verilog and UVM? Anyone have worked in system Verilog and UVM? Okay. So these are the main language and methodologies for verification. System Verilog, UVM, eSpecman, Python, C and VHDL. So this is the evolution of verification languages. Vera or Specman was introduced in 2020 and became the first verification language to cater verification needs. Then verification language was enhanced with new construct to make it more verification friendly, and System Verilog initiative was started by Accelera. Then Cadence Design Systems and Mentor Graphics as a joint effort to provide a common methodology announced the Open Verification Methodology, also known as OVM, for System Design Verilog in 2008. Then to unify all verification methodologies and to enable reuse of verification IP on different simulators, universal verification methodology was introduced in 2010. So we are all familiar with Verilog and Verilog based verification. So why we are going for Verilog to System Verilog for verification? Why we can't use Verilog for complex verification task? System Verilog was introduced for verification in 2002. It was adopted by IEEE standard in 2005. System Verilog was made up of features of Verilog, VHDL and some C and C++ concepts. So why we are moving towards System Verilog from Verilog? System Verilog supports complex test bench structures, and it supports complicated test procedures, and it also supports random stimulus, assertions and coverage. So why we are going for System Verilog? System Verilog support 4 distinct languages under a single simulation. That is System Verilog for design. These are the synthesizable subset. We can use for System Verilog for design. Many of System Verilog subsets are synthesizable. and system Verilog for verification that is done by object-oriented programming subset of system Verilog, and system Verilog for assertion and system Verilog for functional coverage. So we'll discuss this concept later. So this is the system Verilog structure. System Verilog can be used for verification. System Verilog can be used for functional coverage. System Verilog can be used for assertion, stimulus generation, and response checking. The verification aspects of system Verilog is supported by object-oriented programming. Functional coverage is supported by coverage group, cover point. And system Verilog assertions are supported by sequence, property, assert, cover, etc. And they also support coverage monitor. How can you monitor the coverage? It also support stimulus generation, DUT, and response checking. So 1 minute. Okay, sorry. Okay. So we know that in Verilog, we are following direct test or random test. What is the advantages and disadvantages of random test and direct test? Using directed test, we can cover all the cases. But what is the issue with the directed test? For example, our design signal have 4 bits. A single input with 4 bits. What are the possible combinations? 4-bit input may be having 2 power 4 all possible combinations, right? So, if one testing of one combination take 1 millisecond, what is the total time taken? The total time taken will be 1 millisecond into 2 power 4. Assume that we are using a processor with 16-bit or 64-bit. What are the possible combinations? The possible combinations will be 2 power 64. So what will be the time taken for covering all the cases? It will be 2 power 64 into 1 millisecond. That will take a lot of time. So directed test may not be possible for complex SoC design. That's why we are going for random test. So is it possible to cover all the cases for random test cases? That's our question. So there is no optimize or comparison between direct test and random test. In directed test, we can cover all the possible cases, but the simulation time will be very long. For example, if it is a complex SoC design, it will take a lot of years to complete all the directed tests to complete. Hence, we are going for random test. But how can we make random test to cover all the cases? So then we are going for UVM. So what is UVM? UVM is a framework of system value classes from which the test benches can be made. Basically, it's a set of rules. What to be designed, when and how. So the set of rules based on system value classes. So why we are going for from system verilog to UVM? See that we have 3 teams: Team A, Team B, and Team C. Team A is working on test bench 1. Team B is working on test bench 2. Team C is working on test bench 3. So if each teams are following different test bench rules or methodologies, it will be very difficult to combine the process and compatibility, reuse and flexibility. So if all the teams across different companies or different protocols are following the same protocol, we can ensure compatibility, reusability, and flexibility. For example, a company is providing USB protocol and verified verification IP, and another company is using that USB protocol or USB IP and USB verification IP. If they are following different verification protocol, it is not reusable. They need to design another verification IP from scratches, and it is not flexible. So why we are going for UVM? UVM provides scalable, reusable, and interoperable test bench development, and UVM provides a structured methodology that emphasizes scalability and reusability, that provides guidelines for test bench development, and that also provide base class libraries. UVM provide a set of predefined classes, and that also provides verbosity control. That is, UVM provides control over level of details in messages displayed during simulation. Also, UVM provides a set of predefined classes that user can inherit to access built-in functionality. So I think everyone is familiar with the test bench architecture for Verilog, right? So everyone working Verilog, Verilog or UVM, right? So now we are combining a Verilog test bench to the UVM test bench architecture. So this is a Verilog top module. So simple test bench. We have two input A and B, and it is a clock signal, and we are generating some random values, right? So this is the top module. The top module is comparable to the top in UVM or system Verilog. And this is your design. This is a connection between we are instantiating your UUT or design under test. Yeah, very simple, right? And this is your test in this is a test environment in system Verilog or UVM. That is comparable to all the test architecture given in your Verilog architecture. And this is your inputs, clock, A, B, your input values. That is comparable to the driver in UVM environment. And here you can see you are generating random values. You are generating a sequence of random values that is compared to the sequence in UVM or system Verilog. And here is the package. A input signal A and B are given as a package. So that is compared to the packet in UVM. So can you, sorry, it's a sequence, sorry. So are you able to understand the analogy between your system Verilog test bench architecture and the UVM test bench architecture? Everyone is following? So this is the, so if you have any doubts, everyone is following? So, okay. This is the basic top module for UVM. So you have test bench top, test, environment, agent, sequence, driver, monitor, interface, and DUT. So what is UVM test? The test is the top of the hierarchy that initiates the environment component construction. So this is the test that initiate the environment generation. It is also responsible for test bench configuration and stimulus generation. So here a test. So that is responsible for test bench generation and configuration. And we have UVM environment. UVM environment provides hierarchy and container for agents and scoreboards. So we can see that environment consisting of agent and scoreboard that provides all the facilities for agent and scoreboard. And you can see UVM agent. An agent is a container that holds the driver, monitor and scoreboards. You can see that the agent consisting of sequencer, driver and the monitor. That is helpful to have the structured hierarchy based on protocol interface requirement. Then you have UVM sequence item, or it's a transaction. You can have a transaction here. So transaction is a packet that is driven to the DUT or monitored by monitor or pin level activity. So transaction between the DUT and monitor. And UVM driver. The driver interact with DUT. So you can see the driver. The driver interact with the DUT. It receives randomized transactions or sequence item and drives them to DUT. So driver receives a packet item from sequencer, and it is driven to the DUT. And it is also having a UVM sequence. UVM sequence is a container that holds data items. And UVM sequencer, UVM sequence is a mediator who establishes connection between sequence and driver. So you can sequence and driver. So the sequencer will be placed between sequence and driver. And we have UVM monitor. The monitor observes pin level activity on the connected interface at the input and output of the design. So this is a UVM monitor that monitor the pin level activity. And finally, we have UVM scoreboard. So what is the UVM scoreboard? The UVM scoreboard is the actually does the verification that receives the transaction packet from monitor and compares it with the reference model. You can see that the scoreboard for every design we will be having a golden reference. So what does the monitor do? Monitor receive the inputs and the output from the design under test, and that will compare the output with the golden reference model. If the output from the DUT matches with that of the golden reference model, your verification passes. If the output from DUT doesn't matches with the output from the golden reference model, our verification fails. So now we are going how you can apply the AI for design verification approaches. So AI for design verification reduce time to market, improve silicon predictability, identify bugs in the early design cycle so we can save times and money, and optimize design beyond human capability. So where we can apply AI or large language models for verification. We can apply verification for assertion generation, constraint random verification, coverage closure, formal verification, debugging, test stimulus generation, functional safety and security, code generation completion. So we'll see each in detail. So initially we'll see the constraint. What is the constraint? So when I know anyone have worked in system Verilog or UVN constraints? Okay, anyway, we'll discuss some basic concepts. So what is randomization in verification? So in randomization is the process of generating random stimuli input to the stimuli or input as an input to verify the functionality and reliability. In Verilog, we can know that we are using random function. It is generating the random integer values and randomizing the variable alone. So in system Verilog, we can use randomize method. So since system Verilog follows object-oriented programming, we can follow randomize method that is based on object-oriented programming. And we can easily randomize the class properties. Not only the input variables, we can randomize the class and data members of the class. So mainly we can use rand and ranc keyword. So randomization can be done by two keywords, rand and ranc. What is the difference between rand and ranc? Rand generate uniformly distributed over the range, and in ranc, variable values doesn't repeat a random values until every possible values have been assigned. So we'll do some test bench. We'll show some. Okay. So for the time being, for ECC, I'm using EDA background. I think everyone have worked in EDA background. It's a free open source tool for simulation. It is working. It can be used for VHDL and UVM system Verilog and even Python based verification. So I'll share the link to you. This is public. So can you share in chat box?
Yes, sir.
Okay. Okay. You can click in if you're in click in this browser and you can just log in and you'll be able to simulate this idea to understand what is the constraint and randomization. Okay, so we have, okay, so my screen is visible to all. So by using that previous link, you can try this one. So you can see test bench are designed to system log or Verilog. So what we are doing, we have a class package, key1 and key2. And I think you are familiar with the object-oriented programming. We are defining a class. The class name is package. And these are the data members of the class, key1 and key2. And we are trying two methods, one using range and one using ranc. And this is the randomization. Package equal to new, That is, we are initiating the packet. There's a construct, and we are naming this a handle. For this class, we are giving the handle PKT. PKT is the handle for that, and we are randomizing, and packet don't randomize. So what we are doing? We are inheriting the properties of the class packet from here. So we need not repeat all the class properties here. It is packet dot randomize. So can you predict the output for this one? So I'm running this one. So what is the difference here? So you can see that initially we are using ran function. So what happens when we are using ran function? When we are using ran function, this 5 is repeated, right? All the values are not covered. Even though all the values are not covered, the 5 is repeated here. What here when we are using ranc function? When we are using a ranc function, 0, 1, 2, 3, 4, 5, 6, 7. All the possible values are completed. Then only 5 is repeating here. Got it? So if you need to cover all the cases, we can go for ranc. This is output. So we can, these are the randomization. So we can apply at AI tools for initially for randomization. So how which will provide the better output. So outcome we will discuss later. One is constraint and randomization.
വൈകിട്ട് എന്ന് പറയുമ്പോൾ
So we can apply for
ഞങ്ങൾ
AI
7 മണിക്ക്
or
പെരുന്നാളിന് പോകും.
large language for constraint and randomization. So what is constraint?
അത് നമ്മുടെ നടത്തറ ഭാഗ
What is constraint randomization?
നടത്തറ കൊഴുക്കുള്ളി അവിടെ
The constraint randomization is used for controlling the values getting
7:30
assigned on a
8:30
randomization.
വരെ ഒരു
That is achieved by writing constraint for randomization.
ആ അങ്ങനെ
For
ഓക്കെ
example,
ഓക്കെ 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 ശരി ശരി ബൈ.
and we have a random bit key, and what is the range? Range is key should be greater than 5. So I'll share that link also. You can try yourself. So are you, will you be able to get the previous case? Will you be able to simulate the previous one? So can I know everyone were able to try the previous link shared? Hello, am I audible?
Yes, sir. Participants, please respond.
So if everyone were able to simulate the previous one, okay. So I'll share this one. You can try this one also. This constraint. So I have shared the link. You can use this link for you can practice by yourself. So what we are doing here, we have a 4-bit data, and for this we are giving a constraint. The constraint is that the value should be greater than 5. So we can see that all the random value generated are greater than 5. For example, we are giving some value 2. So we can see that all the values are greater than 2.
പക്ഷേ അതിൽ ചോദിച്ചിട്ടുള്ള കാര്യങ്ങളെല്ലാം നമുക്ക് കിട്ടണമെങ്കിൽ സാറ് തന്നെ അത് അപ്ഡേറ്റ് ചെയ്യണം.
So another important concept where AI is applied is assertions. What is assertions? Assertions are the statements that specify a particular. I will cover another also. For assertion, we will show another example. This is an example of ALU. So you might be done RISC-V verifications. So while designing RISC-V or any other CPUs, usually we'll be giving some constraint for the opcode or your instructions. So you can try this one. So these are ALU operands. So the constraint is the sum of 3 operands is less than certain value. So you can see that the sum of operands is always less than FFF. The same way in verification, we can give some constraint to the random values. Then we have assertions. Assertions are the statement that specify a particular relationship between one or more signals or variables. There are 2 types of assertions: immediate assertions and concurrent assertion. The immediate assertion check for condition at the current simulation at a time, and concurrent assertion check the sequence of events spread over a multiple clock cycle. So this is the basics for here. So what we are checking? We have 2 variables. Our assertion is A and B. That is, if A and B are equal, output equal to 1. If A and B are not equal, output equal to 0. So we are giving some values here, A and B. So let us see how the assertions work here. So these are the values given. We can see that A equal to 1 and B equal to 1. Here we can see the assertion passes. And when A equal to 0 and B equal to 0, assertion fails. So when assertion failed here, failed. And A equal to 0 and B equal to 1, assertion fails. And A equal to 1 and B equal to 1, assertions passes. So you can see the output here. So another important concept where the A is applied is coverage. So the main challenge or aim of your verification plan should be increase code coverage and functional coverage while there are no test failures. So what is coverage? Coverage is used to measure the tested and untested portions of the design. Coverage is defined as percentage of verification objective that have been met. So the aim of each verification engineer should be 100% code coverage and 100% functional coverage. So what is the difference between code coverage and functional coverage in verification? Code coverage measures how much of the design code is exercised. This includes the execution of the design box, number of lines, conditions, FSM, toggles, and path. For example, if you have a complex design, it is have multiple design blocks. If all the design blocks have been covered or not, and number of lines, if all the number of lines are code, and conditions. For example, if else statement, for example, case statement will be different case, right? In Verilog, we might be written case 000, case 00, case 0, case 1, case 2, whether all the cases are covered or not. And FSM. For example, we are designing a parity detector, we will be using FSM. So whether we have covered all the states of FSM and toggle and path. The simulator tool will automatically extract the code coverage from the design code. And another is functional coverage. Functional coverage is a user-defined metric that measures how much of the design specification can be exercised in verification. There are two types of functional coverage: data-oriented coverage that check combination of data values have been occurred. And we can get data-oriented coverage by writing coverage groups, coverage points, and also by cross coverage. So we'll see an example. Okay, I'll share that link. You can try this one. So I have shared the link to the chat box. So that will be helpful to understand the basic concept of coverage. So what is here? Input Y is 3 bit. So how many possible combinations are possible? That is 3 bit, 0 to 2. So 2 power 3. 8 possible combinations are possible. Right? So these are the values we are giving here. We can give any values. And we are defining a coverage group, CG, and cover point Y, and we are putting auto min max equal to 4. So we can manually create the coverage bins, or we can automatically create. So this function will automatically create the 4 coverage bins. So coverage is very important topic in verification. Most of the AI models or LLM models try to achieve 100% functional coverage or 100% code coverage. So how the test bench or how the assertions can be modified to get the 100% functional coverage or 100% code coverage. So what does it do? For example, it will create 4 automatic coverage groups. So what are they? So one coverage group will be 0, 1. Another coverage group will be 1, 2. And the third coverage group will be 3. Bin will be 3, 4. And next coverage will be sorry, this is 2, 3. Then 4, 5. 6, 7. Okay. So I am value giving 0, 1, 2, 3. Can I, so this is your bins. So your possible values are 0, 1, 2, 3, 4, 5, 7. We have mapped these values to 4 cases. These are our test cases 0, 1, 2, 3, 4, 5, 6, 7. So this is my input values 0, 1, 2, 3. Can anyone tell what will be the coverage I am achieving here? Can anyone tell what will be the coverage achieved by my design?
50%.
Yes, we can try. Yes, it is 50% coverage. So you can see that 0, 1 corresponding to this bin and 2, 3 corresponding to this bin. Now I am giving 0, 4, 7. So can I know what will be the coverage now? What is the coverage percentage I am achieving now? So it is 75%. Why it is 75%? So 0 corresponding to this bin. So this scenario, so this is already covered. We need not to cover all the test cases. That is, we are dividing the test cases into some subclasses. For example, if you have 2 power 64 input combinations, we may not be able to cover all the 2 power 64 combinations. So we can subdivide or divide the input combinations to some classes. For example, we are designing a 64-bit adder or 64-bit adder or subtractor. So we may not be able to cover all the 2 power 64 cases. it will take a long time for simulation. So we'll subdivide the test cases into some division. That is, we have to cover A equal to positive, B equal to positive. We have to cover a cases where A is positive, B is negative. And we have to cover a case where A is negative, B is negative. And we have to cover a case A is negative and B is negative. B is negative. And during subtraction, we have to cover both A equal to 0 and B equal to 0. And both A equal to -1, both B equal to -1. The same way, we will map all the design cases to sub cases. So we can see that here it is 0, 0. Since it is 0, that comes under 0, 1. So this test case is covered. And 2, 3. There is no input values from this particular case. So 2, 3 is not covered. And 4, 5. There is no, we have a member from 4, 5, there is 4. 6, 7. So there is only, out of 4 bins, 1 bin is not covered. So the code coverage, the functional coverage is 75%. Clear? So this is the basic concept of coverage. And randomization. Another thing is important research that happens in formal verification. There is an important research area, and most of the industries and research are moving towards formal verification. For example, many companies is having its own formal verification group, also a training division for formal verification. Formal verification is a method to ensure that a hardware design behaves as intended by using mathematical analysis or using assertions. In formal verification, we can see that you have formal previous verifications. We followed, the GU-based verifications. But here, in formal verification, we are using mathematical analysis to check correctness of relative to specifications. Traditional verification methods rely on testing and simulation, whereas formal verifications mathematically proves that the design will always functionally correct under all possible scenarios. So this is the basic verification flow. Initially, the design engineers will be making a verification plan. From verification plan, initial coverage metrics are followed. And from initial coverage metrics, random tests are made. So it's an iterative process. From random test, we run the test and we correct the coverage. And we check whether the coverage goals are met. If no, we will identify the coverage holes and we will add the test to the target holes and enhance stimulus generated. And this is the area we can apply machine learning or AI to the verification plan. So the manual design process are very complicated. So we can do manually, but this process is very complicated. They will take a lot of design time and to achieve the verification complete. So we can apply machine learning or AI where we can achieve the coverage goals. And there are already AI-based industrial tools for verification. I think you might have done that. The Versium AI-driven verification platform from Cadence, DSO AI from Synopsys, Solido Generative and Agentic AI from Siemens. All these tools incorporate AI or machine learning to that verification flow, and it is incorporated by many industry teams that provide optimized verification workloads, boost coverage, accelerate root cause analysis of bugs, better, faster, and cheaper semiconductors. But as a researchers, it will be very difficult to there's a limit up to which this tool can be incorporated for extent to an extent. One is license. The license tool is license fee will be very high, and also even though we have a license, these tools are not open source. The code for these tools are not available free, so we can't make changes to their flow. Then, if they have made a model, we need to follow that model. We can't make the changes to that model. If they have done a optimization, we can't change that optimization flow because they are inbuilt. Also, that code is not available. So, as a researcher or engineers, how can you apply our own AI models or our own AI agents to the verification flow? For that, so many open source verification models are available. So many research are going on in open source tools for verification. One is Python. Python is already adopted in industries. Along with TCL script, Python is already adopted for industries for verification, automation, and also for regression analysis. So even though I will see an example, this is a small example, this is not a complicated design, this is simple to analyze. Only to get a view. This is a simple design. This is an example. Okay. So it's a log from VC simulator. We can see that a large number of logs are there. For each design, the verification engineers will be getting a large number of logs like this. So it will be very difficult to manually analyze all these logs, right? This a lot of information is shared this log. So the verification engineers will accept the log from the design from the design engineers, and we will run the test pattern in the design engineers, and that will create logs. So that will create a lot number of logs. So it will be very difficult to analyze each state log manually. It will be difficult. So what we can do? Based on the log, we can generate a Python automation script. So the engineers can written a Python automation script or AI-based tool to manually or analyze the tool. So you can see that this is a report, UVM info. This is a verbosity. That is, we have seen that we have a control of the criticality of the messages we are sharing. UVM info, UVM warning, UVM error. So each verification engineers have to look to this. What is the UVM info? Is there any UVM warnings, and is there any UVM errors and UVM factors? And it will be very difficult to open each that steps, each log, and analyze manually. So for that, we can simply generate a log analysis report. Simply, we can write a Python code to analyze the UVM logs. For example, let me run this one. So you can get a summary. Log analysis report routes. All your log analysis CAV and log analysis files are generated. Also, we got a graphical interface for the log analysis. So you can see that. So out of your cases, 23 passes, 27 fails, 43 errors and failures. And it's your logs report. So we can generate a graphic interface and your log analysis. So what is the, for verification, to machine learning to apply to the verification, we should have a database, right? Data set. So what is the data set for verification? So if any machine learning model, we should have a data set and a training, machine learning model to train and your output. So what are the possible data set for verification AI results? One is your log report, and also your log report from the tool. So there can be follow the data set for your log report from your tools. What are the log report for your tools? And you can extract the features from the using Python. You can extract the required features from the log analysis. For this is a simple case. So you can extract the features using Python or any language using your log from the tool. So you can see that the tool gives so many information, and your code coverage, functional coverage, information errors. From this log analysis report, you can extract the features. What may be the features? Features may be fail or pass, your functional coverage, code coverage, and this may be given. The features may be given to your machine learning models. Even the Python can be used for, the industries are using for Python for mailing. For example, you are receiving these logs from design engineers. For example, this log corresponding to the design from engineers 1. This log is obtained from design engineers 2. This log is received from design engineers 3. So we need to mail the error report corresponding to this design engineers to this design engineers. And we need to cover the report corresponding to design engineers to more design engineers 2. So that will be very complicated process. For example, we have 10 engineers, we have to mail to 10 engineers manually. And we have to find the design report, verification report. That is very, so using Python, we can automatically select the design log and we can automatically send the design report to the engineers. So Python can even use it for automatic mailing. So this is some of the open source tools for verification. CocoDB. So many engineers are working on. There's a lot of open source team working to create a open source verification environment for verification that is compatible with the industrial verification environment. Although also the industries is also supporting the even CocoDB team. For example, Cadence, Synopsys, and Siemens are supporting free license to the support to the CocoDB design engineers team. Not to everyone, not to every engineers and students. For the CocoDB engineers team, they are providing free license. so that they can test the CocoDB or Python environment in their tools. So CocoDB is a open source coroutine based co-simulation test bench environment for verifying VHDL and system Verilog RTL using Python. What is coroutine? Coroutine that lets us write code and concurrency waiting for an event scheduling multiple tasks. Mainly it is used for synchronization. And PyUVM is the universal verification methodology that is implemented in Python instead of system Verilog. PyUVM uses CocoDB to interact with simulators and schedule simulation events. So another environment that is used for open source verification is Verilator. There's an open source system Verilog simulator, Lean system. And we have Icarus Verilog. Icarus Verilog is a free compiler implementation for hardware description language. I think you might have used it for this one or this one. Also coverage. Coverage is major important issue in open source verification. Most of the industrial tools like Cadence, Synopsys have good coverage support for their tools. But the verification teams are, the open source verification teams are still working on to get better coverage for open source tools. CoverView and PyVSC are the verification coverage, are the major important source to coverage. PyVSC is a Python library that implements random verification stimulus generation and coverage collection. So for open source verification, Verilator and PyVM are using. They support massive simulation speed. There is no need for license. They can be easily scaling in cloud environment and DP access and Python native test orchestration. For example, Python provides many libraries, so that libraries are very helpful for verification. And async safe concurrency pattern and deterministic reset safe behavior. That is, we have a control over reset for verification. Even though open source verification is improving, there are so many open source challenges. Coverage closure is still an industry gap. We couldn't still achieve coverage that is compatible with the industrial tools because we could not coverage system level coverage group, cross coverage, weighted distribution coverage, and vendor coverage merging reporting. So the industries who are working on the researchers who are working on EDA tool generation or EDA, they can working on coverage to the how can you achieve coverage to the team because still the open source tools teams are yet to achieve a good coverage tools. And DPA, the direct programming interface, falls behind very large simulation because Python have to interface the C++ and to the HDL bus functional models. So the transaction will be very dusty and configuration flow. Another challenge is debugging tools. We know that most of the industry tools provide. So if anyone have any doubts, can I move forwards? So there is waveform entry, GUI driven. For example, you might have used in Cadence, Synopsys, etc. They all provide the a good GUI for verification.
Staff, ಎಲ್ಲೋ ಸ್ಟೂಡೆಂಟ್ಸ್
Hello?
ಏನಮ್ಮ ಆರೆಂಜ್ ಕಲರ್ ಎಲ್ಲ ಸ್ಟೂಡೆಂಟ್ಸ್
Hello, yes. Okay.
ನಮ್ದು ಬ್ಲೂ ಮತ್ತೆ ಕಾಫಿ ಕಾಫಿ ಬ್ಲೂ ಗ್ರೀನ್ ಗ್ರೀನ್ ಲೈಟ್ ಗ್ರೀನ್ ಕಾಫಿ ಕಲರ್ ಅಲ್ಲ ಲೈಟ್ ಗ್ರೀನ್ ಸರ್ ನಮ್ದು
Hello,
ಬ್ಲೂ
any?
ಅವ್ರದ್ದು ಲೈಟ್
Hello.
ಗ್ರೀನ್ ಗ್ರೀನ್ ಕಾಫಿ ಕಲರ್ ರೆಡಿ ಮಾಡಿತ್ತು
Hello, any?
ಗ್ರೀನ್ ಟೈಪ್
Any doubts? Can I move forwards?
ನೋಡಿ ಎಲ್ಲರೂ ಐಡಿ ಕಾರ್ಡ್ ಹಾಕೋದು ನೋಡಿ ಇಲ್ಲಿ
Also for standard protocol AFC APB. So there is no support for standard protocols. Standard design IP and verification IPs are still working on Verilog system Verilog. For example, most of the design IPs and verification IPs are still based on UVM system Verilog. So we need a standard protocol based on open source. And runtime limitations of Python. For ultra high frequency event driven simulations, Python layers can induce overhead. So let us see how AI can be applied for design verification. So the training data is input stimuli, coverage means status constraint, input and output from DOV and test coverage. And we can apply machine learning models such as linear, ANN, DNN, or RF. So we know that each machine learning model will be having input, machine learning approach and outputs. So your training data will be input stimulus, coverage means status, constraint, input and output, test configuration and test parameters. And contribution may be simulation startup, functional coverage, code coverage, and test reduction. So this is general work where AI is used for verification. So in PyVM testbench, we are generating sample values of some randomized signals and cover with heterogeneous information. And
ಎಕ್ಸಾಮ್
we can apply supervised machine learning and machine learning optimization,
ಎಲೆಕ್ಟ್ರಾನಿಕ್ಸ್ ಅಂಡ್ ಡಿಜಿಟಲ್
and we can apply the coverage regain. And we are checking the coverage, and if coverage based on the coverage and machine learning model, we can modify the test bench. That is the automated test. Thank you. I'll show.
ಅಲ್ಲೇ ಅದೇ ಅದೇ ಅಲ್ಲೇ ಮಾಡಿ
Shahina ma'am, can you please mute your mic?
ಅದೇ ಇವತ್ತು ಹೋಗೋದು ಕಮ್ಮಿ ಅನ್ಕೊಂಡಿದೀವಿ ನೋಡೋಣ ಸಿಕ್ಸ್ ನೆನ್ನೆ ಬೆಳಿಗ್ಗೆ ಕಾರ್ಗಿ ಅಷ್ಟು ಆಪೋಸಿಟ್ ಹೋಗ್ತಾರೆ ಸಖತ್ ರಶ್ ಇತ್ತು
Okay, so
ರಜೆ ಇದಲ್ಲ ಸರ್
having the
ಮಂಡೇ ರಜಾ
open source verification in settings my system. So I'll show a simple
ಸಿಕ್ಕಿರುತ್ತೆ
video.
ഹലോ
ಕೆಲವು
സാറേ
ಟ್ರಿಪ್ ಪ್ಲಾನ್ ಹಾಕೋ
ഹലോ
So
അതെ സാറേ ഒരു
we can do verification using iCars Verilog
മ്യൂട്ട് ചെയ്യാൻ പറഞ്ഞിട്ട് മ്യൂട്ട് ചെയ്യണില്ല
or using the
സാറിന്റെ മെയിൽ ഐ ഡി കൂടെ ലോഗിൻ ചെയ്തിട്ട് മ്യൂട്ട് ചെയ്യൂ
Verilator. So initially using
Right.
Semiconductor.
ഷഹാന
ಟ್ರೈನ್ಸ್
So
ಇದೆ ಕಾಲ್ಗಿದೆ
you can do make once we have done Coco TV, PyVM, and regression supporting
ಗಾಡಿ
packages,
ಬಸ್ ಸ್ಟ್ಯಾಂಡ್ ಅಲ್ಲಿ ಬಿಟ್ಟಿದೆ
we can support make Semiconductor iCars.
ಮತ್ತೆ ಅದೇ ಎತ್ಕೊಂಡು ಹೋಗ್ಬೇಕು
So they will give the all verification results. and also we can give the simulation very later. So this is a simple demo of the open source verification team. Okay, thank you. If anyone any doubts,
Anyone have any doubts?
yes. Hello, anyone have any doubts? So
Thank you so much,
thank.
sir, for a clear
Okay,
and structured explanation. I extend our sincere, heartfelt gratitude for your valuable presence and insightful address. Thank you, sir.
okay, thank you, thank you, thanks for the opportunities.
Thank you.
Okay, thank you.
For next session, Sharanam will be joining soon.
അതെ സാറേ, അടുത്ത ഹലോ. ആ, ഓക്കെ 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 ഓക്കെ. പോയ അടുത്ത് കിട്ടില്ലേ, അതാണ് വേറെ വിറ്റ്. അല്ല സാറേ, അത് മിസ് വന്നിട്ടില്ലല്ലോ. ഇല്ല. ഓക്കെ ഓക്കെ. അല്ല സാറേ, ആ അത് പറഞ്ഞിട്ടുണ്ട്. അത് പറഞ്ഞിട്ടുണ്ട്. ഓക്കെ 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 ഓക്കെ. ആ
Yes, sir. Yes, sir. There is one more session. Sharon ma'am will join within 5 minutes.
നിനക്ക് അവിടെ ഇങ്ങനൊരു നീ അതിനൊക്കെ വീടാന്നല്ലേ പറയണേ, ഞാനൊക്കെ ഇനി ഹോസ്റ്റലിനെ പറയുള്ളൂ.
Sharing is good evening.
Hello. Am I audible?
Yes, ma'am, you're audible.
Okay, thank you. So good evening. Good evening all. I am Sharon. I am working as scientist E in C-DAC, Thiruvananthapuram. So let us start the session. So let me share my screen. So screen is visible.
Yeah, ma'am, it's visible.
Okay. So now our this session we are going to discuss about Vega processors and SOCs. So I am from C-DAC, Center for Development of Advanced Computing, Trivandrum branch. So agenda of our session, that is, first is introduction to C-DAC, a brief introduction to C-DAC, and a brief introduction to Digital India RISC-V program, and Vega series of processors we will discuss. Then Astra IP portfolio we will be discussing. Then after that we will be seeing what are all the SOCs based on Vega and what are all the development boards that we have developed under the ADIS, under the name ADIS. Then ADIS development board programming. Then we will see how to purchase this SOCs under what are all the support system that is available for this SOCs. So my screen is visible, right? So now I am going through the agenda screen.
Yes, ma'am, your screen is visible.
Thank you, thank you. So Center for Development of Advanced Computing, it is a premier R&D organization under Ministry of Electronics and Information Technology. We actually carry out application-oriented R&D in the field of IT, electronics and associated areas. So we are having our presence all over India. We are having 12 different centers starting from North, Mohali, Noida, Delhi, Patna and Northeast. We are having center at Silchar, Kolkata, and in the mid of India we are having Mumbai, Patna, Hyderabad, and towards the south we are having Bangalore, Chennai and Thiruvananthapuram. So I am from Trivandrum Center of C-DAC. Trust areas of C-DAC. So from the agenda slide itself, you would have understood we are actually developing Vega series of processors. So we will see what are all the Vega series of processors and all. So in addition to Vega series of processors, we are actually working. We have actually started working on high performance computing. That was the starting of C-DAC. We are actually working on high performance computing and cloud computing. So under which we have actually developed the current series of supercomputers, and we are continuing our research in supercomputer development under National Supercomputing Mission of India.
Okay.
So next our trust area is strategic electronics.
Okay, okay.
So in strategic electronics, we actually
Okay,
work for defense, space, as well as
okay, okay.
electronics
Perfect.
field, normal consumer electronics also. So in the case of defense, we have developed the auto gun shoot detection system, and in addition to that, we have developed we are actually working we are having different groups here in from power electronics group. They are working on locomotive units, development of locomotive units, a control unit
Okay,
for
great, great.
locomotive that is being deployed in many locomotives in Indian railways.
Wow.
Around 600 to 700
Okay.
locomotives, this control system has been uh, deployed. Then, in addition to that, we are working on the
Where
hospital
we see
management
that in the
system,
portal.
traffic management and control system that is being deployed in different cities all over India. So that and all comes under the strategic electronic group. Then, if you are coming
That's really great.
looking into the software technologies, so under this we have developed a emergency response system. I think you would have heard about emergency response system 112 that is being deployed all over India. For any emergency, you can call and you will get an immediate response. That system is being deployed all over India. That is one of the thing that we have done. So, in addition to that, in uh,
It is
health
mandatory.
sectors also different hospital management systems, telemedicine technologies that has been uh, deployed. Then the major achievement we have done in the mass cervical cancer
The exam link.
detection system that we have done for
It
rural
will
people
open at
actually.
8 o'clock.
Uh, then if you are coming to the cyber security
Yes.
division, they are closely
Again.
working with police as well as different agencies such as police as well as CBI for the for with our indigenous products that helps for the disk forensics, network management system, etc. So we are helping on that area also, and we have started working on the quantum computing, which is an emerging technology in this current area. So in that one also we have started working. Then we are having health and means health informatics that we have already discussed. Then we are having a good experience in multi-language computing and heritage computing also. In addition to that, we are also working for the education and training. We are conducting various MTech courses and short-term courses also we are conducting in different sectors for embedded systems, VLSI, etc. Cyber security and all. So this is the trust areas of C-DAC. Overall, what all the areas we are working. So these are the various products. We can see Vega processor is one of many products. 112 that we have already seen, that is a emergency response system that is deployed all over India. In addition to that, AX is there, ENOS is there, the E-Sanjeevani is there, that is a emergency blood bank management system. So these are the different products that are being given by C-DAC,
Participants should.
and Vega processor is one among many. Hope all of you are clear up to
Yes.
this. So let us start with let's go for the next slide. So before going to Vega processor, would like to have a brief introduction to how we came, how we achieved this Vega processor. So in recent past, there was there is a vision from our government, that is Atmanirbhar Bharat. Atmanirbhar Bharat means making India self-sufficient in the field of in all field, especially in the field of electronics. So all of you know that we are actually depend on other countries. We are actually importing things. Any consumer electronics that is being that we are importing, that we are depend on the other countries. So how to make India self-sufficient in the case of consumer electronics. So wherever we see many electronics items, we can see, right, the laptop we are using, mobile phones, storage system, uh, anything, supercomputers also, anything, it is consumer electronics that we are depend for other countries. So this vision came from our government, and we have given given, that means not only C-DAC, many organizations have requested to come up with a roadmap how to make India self-sufficient in the field of microprocessors. So why we have chosen microprocessor? Is there any special reason that microprocessor is being chosen? So if you are seeing any consumer electronics, whatever be the consumer electronics, what is the brain of that consumer electronics? It will be the microprocessor or microcontroller. Whatever thing you are seeing. So from simple consumer electronics such as mobile phone or any storage system, hard disk or flash devices you are using. So basic element is the microprocessor or microcontroller. For that one itself, we are depending on some other countries. So how to make India self-sufficient in the field of microprocessors? That was the mission, and under this, several organizations have given a chance to come up with the microprocessor. So that program is the Digital India RISC-V program. RISC-V is RISC-V based processor we have to develop for our India. So in that during that process, it is in the process of several years. Finally, C-DAC has come up with India's first indigenous microprocessor, SoC, and that is microprocessor is Vega series of processors we have developed, and SoC is Tejas, Tejas 32, Tejas 64, Dhruv, Dhanush. These are the series of SoCs that we have developed. So the mission of this one is to make India self-sufficient in the field of electronics. Not only India being the self-sufficient, India should be the hub of all electronic devices, especially microprocessors. India should be the hub of microprocessors. Not only for India, it should be a provider for this microprocessor all over the world. So based on that, this Digital India RISC-V program was introduced, and with the help of the Digital India RISC-V program, in short it is called as a DIR-V program, we are able to come up with the Vega series of microprocessors. So as part of the Digital India RISC-V program, C-DAC has developed series of microprocessors under the name Vega processors. These high performance microprocessors are based on open source RISC-V instruction set architecture. Okay, so till now it is clear, right? So we have based on our Atmanirbhar Bharat, a program is being given by the Ministry of Electronics and Information Technology, that is DIRFI, with the help of DIRFI sponsorship, we could able to come up with Vega series of microprocessor. So what are all the microprocessors that will come under the Vega series? So till now we are having different flavors of Vega processor, starting from Vega ET1031, which is a single core 32-bit 3-stage in order processor. So there is a naming structure is there. E, this first letter E after Vega, whatever first letter is there, E, that is stands for embedded application, and T stands for 32, and 1 stands for number of cores. You know now there can be a single core processor or multi-core processors also. Then that 03, that stands for number of pipelines, and last one that stands for version number. So Vega ET1031, that is a 32-bit, as is this T stands for 32-bit, and it is a 3-stage. This 03 that represent how many pipelines are there, how many stages are there for each processor. It has to do fetch, decode, execute, and all. So that's stages. It is actually a 3-stage processor, and in order means it will be a sequence. It can execute the instruction in sequence. Whatever instructions is given, it is executing the instructions in the sequence which is being given, and it is a single core. This 81, that stands for the number of cores. Then that is the first Vega series, Vega ET1031, that is a 32-bit 3-stage single core processor. So next we move to Vega AT1051. So Vega AT, that is application 32. It is an application processor, whereas ET is the embedded processor, means small scale applications. Then it is AT1051. It is also 32-bit, but number of pipeline stages, it is 5-stage in order single core. So once that is being achieved, then we move to Vega AS1061. A, that is application, S stands for 64. So this is a 64-bit processor. So initially whatever 2 processor that we have seen, that is a 32-bit processor, and now it is a 64-bit processor. This is also in order instruction execution, and it is a single core processor. So now next we come up with the Vega AS1161. That also AS means AS stands for application, S is for 64-bit, and this one stands for, first one stands for number of cores. So it is also a single core, but the 16 stands for number of pipelines, and this last one stands for version. So this is a 64-bit 16-stage out of order single core processor that we have developed. Next we will move on to Vega AS2161, which is also again 64-bit out of order. Only difference is that AS2 stands for number of cores. So this is a dual core processor. Other one is Vega AS4161. 41, this 4 stands for the others. Here it is same, right? Number of stages from here, that is 16 and 16, 1 is same for last 3. Only difference is one is 64-bit, the other one is 64-bit. One is 64-bit single core, the other one is 64-bit dual core, and the last one, that is 64-bit quad core. So these are the Vega series of processors that are presently available. So our aim is to achieve quad core processor. So we started our journey with Vega ET1031, that is a 32-bit processor. Into the internals of 32-bit Vega ET1031 processor. So as we have already seen, it is a 32-bit processor, and each processor will support instruction sets, RISC-V instruction sets, ISA. So this Vega ET1031, it supports RV32 RISC-V, it is 32-bit RISC-V instructions it will support. IM, integer, that is basic integer instructions, and M, it stands for multiply and division. So this one will support basic integer as well as multiply and division instructions. So it is a three-stage in-order pipeline, Harvard architecture. It has a high-performance multiply and division unit, and it supports the vectored interrupt. So from peripherals, whenever a peripheral is want to generate an interrupt, it will give a specific number with which the processor can understand which peripheral is giving that interrupt, which is the cause of that interrupt. So that is the vectored interrupt support. It is also supports the free RTOS compatible. We can run free RTOS in Vega ET1031. If you are seeing into the architecture, the same thing. It is having a tightly integrated memory. In addition to the processor, in addition to the 32-bit processor, it is having a debug and interrupt support, and tightly integrated memory is there, and AHB or AXI interface through which memory and peripheral ports can be connected. So this is the internal architecture of ET1031. So next processor, that is Vega AT1051. So as we have already seen, A, that is stands for application, and T stands for 32. So this is a 32-bit processor. This one stands for single core, and 05, that stands for pipelining. So this is a RISC-V. It supports more instructions other than integer and multiply and division. It supports atomic, floating point, as well as compressed instruction set it is supporting. So this is a 5-stage in-order pipeline implementation. So this also, it is in order, and it is having a memory management unit, and it is having a branch predictor unit, 8 KB L1 cache and 8 KB D cache is there. It also supports more operating systems, means basic operating systems such as Linux, Zephyr, as well as FreeRTOS compatible. So as it is supporting single point, the F stands for floating point now, that so it is having a floating point unit also, in addition to the 32-bit processor core. It is having branch predictor, memory management unit, interrupt support, floating point unit, and L1 TLB. We can connect peripherals via AHB or AXI4 interface. So next is our 64-bit Vega series, that is AS1061. So it supports all the instructions, ISA instructions, that is integer, multiply, division, atomic, single precision floating point, and double precision floating point, as well as compressed instruction set. It is 6-stage, as the 06 stands for 6-stage pipelining. It is also a Harvard architecture. It is having a high performance multiply and division unit. It supports vectored interrupt, memory management unit is also the then branch predictor, and 8 KB L1 and D cache is there, and it supports the operating systems such as FreeRTOS, Linux, and Zephyr. It is compatible. So only difference is that only difference between the Vega AT10 1051 and Vega AS1061 is only the processor is in AT1051 it is 32-bit processor, here it is 64-bit processor. Remaining, it remains same. Hope you are able to follow this, right? Okay, next is Vega AS1161 series of processor, where this AS is application 64, this single core, this is also single core, but only difference is that it is 16-stage pipeline. So 16-stage out-of-order pipeline, it is having a MMU, Harvard architecture it supports, branch predictor, and there is a difference in L1 and L2 cache. That it is actually 32-bit, 32 KB L1 cache and 32 KB D cache it is supporting till the previous one AS10. Okay, AS1061 it was 8 KB L1 and L2 cache. Here it is supporting 32 KB L1 and L2 cache. It is having a floating point unit as it is here it is supporting single precision floating point as well as double precision floating point, and via AXI, AHB and AC interface the memory and peripheral boards can be connected. Memory peripheral devices can be connected. So during the course of development of Vega processors, so we can see Vega processor is having a processor core. In addition to the processor alone, it cannot work, right? It will have different peripherals also, peripheral devices all together. It will be working. So processor has to interact with the memories such as RAM, and it has to perform the operation and has to give some outputs to GPIOs or UART, USB like that. So for the development of this Vega processor, so we have developed many IP cores also, so that that can be integrated based on the customer application to develop a customer specific SOCs. So these are all the system IPs that we have developed. ERPLIC, that is interrupt controller, ERDMA, that is direct memory controller, direct memory access controller, DMA controller. So that are the system IPs, and peripherals that are USB host and device controller, host or device controller, Ethernet map, that is 10 bar 100 Mbps IPs we have developed. Ethernet gigabit Ethernet map IPs also it is being developed. Configurable timer IPs were also developed. UART IPs developed. Then SPA, I2C, PWM, GPIO, SD card controller. So these are all the different IPs. Then static memory, SMC controller, static memory controller, through which we can connect different memories such as SRAM, NOR, etc. So these are all the IPs that we have developed as part of Vega processor. So once the Vega processor is ready, and so once the processor is ready, we have to go for a SOC, right? Processor is ready means processor along with some peripherals will form a SOC, and we have to make a silicon. We have to get the silicon of the silicon that we will call as an SOC. So we have developed the Tejas 32 SOC. That is our first tape-out. It is from Siltera, Singapore. It is with the technology 130 nanometer technology that we have developed. And in recent past, 2025, we have developed the Tejas 64 SOC also. That is from SIL. that is actually fully indigenous processor. That is actually a fully indigenous processor. Means tape out everything. It is being done in India itself with SEL 180 nanometer technology. And Drew 64 that we have done with TSMC Taiwan with 28 nanometer technology. So that is the latest one. And now we are working for our Dhanush, which is a quad core processor. So Tejas 32, that is a single core 32-bit processor. Tejas 64, it is single core 64-bit processor. Dhruv, that is dual core 64-bit processor. Dhanush, that is quad core 64-bit processor. So now we will have a look into Tejas 32 internals. So Tejas 32 Vega processor that we have used is Vega ET1031 that supports RISC-V IM instructions. I, that is the integer, and M multiply, basic integer and multiplication it will do. So in addition to that, it is being connected with a similar to APB interconnect through the APB similar to APB interconnect. It is a specific interconnect through which all the peripherals such as timers, it is actually integrated with 3 timers, 8 PWM, 32 GPIOs, and 3 I2C, 4 SPA, 3 UART, and RAM, it is 256 KB RAM, and boot ROM is also there. That boot ROM, you know, na? RAM means if we are keeping the program into the RAM, it will each time we have to, whenever the power is off, program will get lost. So it is having an onboard flash also, boot ROM also, it is internal intercontroller is there. So these are all the peripherals along with the ET103 1031. It forms the Tejas 32 SoC. So this is the pictorial representation of what all the peripherals are there. It is actually a single core. SRAM is a timer, SPA, I2C, PWM, GPIO, ROM, UART is there. And it can operate up to actually 125 megahertz the core can operate. So up to 128 megahertz the core can operate. Just a minute. Yes, sorry. So let us continue with our Tejas 32 SoC. That is, so this is a pictorial representation. What all the peripherals it is having in addition to the CPU core processor. So if we are seeing, you know, Vega ET1031 is the processor. RAM is 256 KB. So as RAM size is less, we can run small applications into this. It supports 3 number of UARTs, 4 SPAs, 3 timers, 8 PWMs, 3 I2Cs, 32 GPIOs it supports. Core voltage is 1.3 volt. What is the operating voltage of core? And IO peripherals means all the IO pins, it is 3.3 volt IO pins, and it can support up to 125 megahertz. So it can use for variety of applications such as sensor fusion for collecting data from different sensors, smart meters, system supervisors, remote sensors, small IoT devices. Because of the small IoT devices means 256 KB RAM is there. So The RAM size is limited. For small applications we can use. For all small IoT devices, wearable devices, toys, etc., industrial networking, and many more applications, we can go ahead with Tejas 32 SoCs. So once SoC is with SoCs, in order to work, we should have a development board. So this is our ARIS development board. All boards that is based on the Tejas SoCs that we have named under different ARIS boards. So this is ARIS version 2 board. So basic processor is Vega ET1031 with with the RAM, and as it is having a flash of 2 MB flash, and it is having 3 USBs, 3 SPAs, 3 timers, 8 PWM, 2 I2C, 4 channel ADC, 32 GPIOs, etc. It is operating at 100 megahertz. So this is actually you can see this similar to size card, or the size of the development board is little bit big. You would have used Arduino Uno board. It is slightly comparable to Arduino Uno board, slightly bigger than the Arduino Uno board. So if we are going for in some wearable applications and all, for that one we have developed a micro board. So micro ARIS micro board, which is also based on Vega ET1031 only. Remaining things and all it is same. We have reduced the GPIOs to make the board development board more compatible. It is also operating at 100 megahertz. We can see from previous to this means Arduino V2 board, it is having a 32 GPIO pins. The GPIO pins have been reduced, and onboard some switches and all it is being reduced to reduce the size, and connectors also it is being reduced, so that it can use for small size applications, wearable application or a compact device. Next is ARIS IoT development board. So basic thing is this is also all are based on Tejas 32 SoC only. This SoC is Tejas 32, which is based on Vega ET1031. This RAM, ROM, flash, UART and all remains same. Only difference is that it supports some onboard devices such as Bluetooth and Wi-Fi module. It is having a Bluetooth and Wi-Fi module onboard module is there, and few sensors it is having: digital proximity sensor, ambient light and gesture sensor. It is having 6-axis digital accelerometer, as well as gyroscope sensor, gas, humidity, pressure, temperature sensor. It is having piezoelectric buzzer. It is having, and potentiometer for ADC input. So in order to vary the ADC input, here we have provided the potentiometer. Then 2 push buttons and 2 LED indicators it is having. So this board is best suited for any IoT application, as it is having a through Wi-Fi module we can connect to internet. So for IoT application, this board is the preferred one. Vega, that is ARIS V2 development board. It is similar to ARIS V2 development board. V2 development and V3 are similar, but V3 is bit cost effective. Cost effective version for students and for that specific application only we have developed a Vega V3 board. And one more board is the which is more cost effective, that we will see. So next is ARIS Alpha development board. So Alpha development board, it is actually supporting CAN Ethernet SD card. So in addition to all other features remain same. In addition to the existing features, it support CAN. It is having a standalone CAN controller is there, and Ethernet controller, standalone Ethernet controller is there on the board it is having, and SD card reader is also it is inbuilt on the board. So for if you want to connect it to the LAN and all, you have to go for this Alpha board, or if you want to use an SD card for your application, then this one is the preferred board. Then for making the board more compatible, for that one this this dot board is being developed. This here most of the peripherals are remain same except GPIOs we have reduced them, and timer, okay, SPI UART, number of UARTs also in basic thing is 3, so number of UARTs here we have taken only 1 UART and 2 SPI and 3 timers only we have taken, and ADC channels it is as usual, it is for the so remaining peripherals whatever taken out to the board that is being reduced, and we made a dot board which is a most compatible ADC board that is available. So this eco development board, it is this is the means with for a school and college applications, means for a normal basic embedded application, this is more suitable, and it is cost effective also. It is also based on Tejas 32 SoC, that is Vega ET1031. Peripherals and will almost remain same. Only thing is that the few peripherals that has been taken out, that is being reduced. So all peripherals we have given, but with the limited number of quantities that is being taken for this particular board. Then we are having Nova board. So Nova board, it is you have seen the IoT board, right? So this is the cheaper version of your IoT board. It is having onboard Bluetooth and Wi-Fi module. It is there with limited peripherals such as 3D accelerometer and gyroscope. It is having, and cryptographic chip is also onboard cryptographic chip is also there. All other all the processor, that is Vega ET1031, all remain same. RAM, flash, this is an onboard flash, that is 2 MB. Peripherals and all, it is limited to one UART, 1 SPA, 3 timer, 8 number of PWMs, 1 I2C. ADC is limited. GPUs actually it can support up to 32. Only 14 GPU pins have been taken to make it compatible. Means this is a compatible version of IoT board. So till now what we have seen is Tejas 32 SoC. So now we are going to see the details of Tejas 64 SoC. So Tejas 64 SoC is based on Vega AS1061, that is a 64-bit 6-stage processor, 6-stage pipeline processor. So this is the AS1061. It is being connected to the peripherals through AXI interface, AXI interconnect. So through AXI interconnect, debug module, SD-RAM, Ethernet, interrupt controllers. These are the peripherals that are add-on to Tejas 64 SoC. In Tejas 32, we have limited peripherals, right? We have boot ROM, RAM, and UART, GPIO, timer, like that. Limited peripherals are there. In 64, especially this SD-RAM controller, debug module, 1 gigabit Ethernet, interrupt controller, that is being added, and through AXI to APB interface, I2C UART, 4 UART SPA, QSPA, GPIOs, timers, and watchdog timers are connected in Tejas 64 SoC. So this is a pictorial representation of what all the peripherals are there along with the processor. So it is a single core. So if you are going to the details of Tejas 64 SoC, it is a single core Vega AS1061 processor. We support single and double precision floating point, and it is having 8 KB L1 cache and 8 KB data cache, and internal RAM is 128 KB, which was 256 KB in the case of Tejas 32. But here we are also supporting a DRAM, 256 MB DRAM, so that we can get a better memory size. So So in addition to that, we are supporting a 64 MB QSPA flash support as well, so that we can run most of all applications in this. And it is having a gigabit MAC is there, multi-channel DMA it is there, and it is having a display controller also. Means if we want to have a small display to be connected to our application, means we want to display your sensor value along with the board itself, so you will interface a display module along with your board, so that display module can be directly interfaced. So display controller is also there. It is having 8 timer, 4 UART, 1 QSPA, 1 SPA, 8 PWM, 8 timers are there, I square C, then GPIO, I square S, IO voltage is 3.3 volt. For all core, the IO voltage is 3.3 volt. Core voltage is 1.1 volt, and its operating frequency is 80 to 100 megahertz. So now we will go for Dhruv 64. So Dhruv 64. So till now, what all things we have seen? We have seen Tejas 32, which is a 32-bit single core SoC. Then we have seen Tejas 64, that is a 64-bit single core SoC. Now we are going to see Dhruv 64, which is dual core 64-bit SoC. So this is the internal architecture of a. So this is based on AS2161, Vega AS2161, 64-bit high performance processor for embedded application. So this is all this is recently tapered in TSMA, Taiwan. This is the SoC. So in addition to the processor core, you can see two processor core is there. So along with that, different peripherals it is supporting. So it is having a inside the SoC itself, we are having a display controller. So this is specific to Dhruv 64. Where in Tejas 64, it is an onboard. Means on the board only the display controller support. Onboard display controller is there. Here in SoC itself, the display controller is inbuilt in the SoC. So along with that, it is having a debug module, SMC controller. It is being added here. Then Ethernet, 1 gigabit Ethernet. It was already there in Tejas 64 itself. USB it is being added. SD card it was there. Then eMMC controller that is being added. Interrupt controller, boot ROM, RAM. Then PWM through AXI to APD, PWM, UART, QSPA, SPA, I square C, GPIO, timer and watchdog. This is almost similar to Tejas 64 SoC. So Dhruv 64, Dhruv 64 operating frequency is 1 gigahertz actually. So that is the performance wise, it is 1 gigahertz. And it is super scalar out of order. It is actually supporting out of order instruction execution. So this is an overall diagram of Dhruv 64. It is having dual core, it is having display controller, PWM, GPIOs. Remaining are almost similar. That is special peripheral that is being added is eMMC controller. Then DDR4 controller, it is having DDR4 controller. USB OTG it is being added. Quad SPA also it is being added. Display controller. So these are the specific IP codes that are being added as part of Dhruv 64. The main difference between Dhruv 64 and Tejas 64 is one is operating frequency, where Tejas 64 supports 100 megahertz, where Dhruv 64 supports 1 gigahertz, and it had add-on peripherals also, such as USB OTG controller. 2 USB OTG controller is a SD host controller. It was already there in Dhruv 64 as well as Tejas 64. eMMC controller it is being added. That DDR4 memory controller, it is an add-on peripheral in Dhruv 64. And Dhruv 64 it is 16 KB L1 cache as well as 32 KB D cache, and 512 KB shared L2 cache is also. Peripherals peripherals that we have already seen. It is similar to that one. Similar to Tejas 64, almost similar to Tejas 64. So now we know C-DAC is having Vega series of processors. Vega series of processors are the then Aries boards. Aries boards different versions are there. V1, V2, V3, as well as micro board is there. Dot board is there. So how to use that one? What is the Vega ecosystem that is being provided? How we can use this one? How we can actually use India's indigenous microprocessor for our school projects or uh, industrial projects. So for that one, we are actually what all the things that is needed is we are actually supporting with the Arduino IDE. Only thing is that you have to add a Vega board support package is separately available in the Vega processor website. So you can add that ID that board support package to your Arduino IDE and you can start using your Arduino IDE. Similarly, you are using the Arduino IDE. Only you have to add the board support package for Vega. Then Eclipse based IDE is also we are supporting for Vega processor. Operating systems Linux, Zephyr, FreeRTOS, Fedora, and Debian operating systems that can be ported to our SoC. Linux device drivers we are supporting. Board support packages are also there. 100 plus libraries have been developed for different IoT application, compiler tools, documentation, discussion forums, tutorial videos are there to support for interfacing each peripherals, each sensors. So these are all the Vega ecosystem that is presently available. For support, you can go for www.vegaprocessor.in and you can mail at vega@cdac.in and you can contact for any in-person direction is required. You can contact in this number. So for more information channel, YouTube is there in Vega Processor, LinkedIn is there on Vega Processor, Twitter, Instagram. So these are the some useful links. For website, you can go for www.vegaprocessor.in. So you can go through the YouTube in vegaprocessor.in and discussion forum you can contact. Vega blogs are also there. LinkedIn, via LinkedIn you can contact. So you can go to introduction to Vega processor video is there. So for further reference you can use that one. So before concluding, so let us have a quick revision what all the things we have seen. So uh, okay, we have already seen Vega series of processors. Different Vega series of processors were there. Vega based SoC that we have seen Tejas 30, Tejas 32, Tejas 64, Dhruv and Dhanush SoCs we have seen. A Vega development boards we have seen that varieties of development boards are there. Based on your application, you can choose the smallest means form factor board, that is a dot board. To IoT application, if you want, there is a specific IoT boards are also there. So what are all the applications you can use for this Vega boards or Aries boards? So almost all embedded application you can use our boards. In addition to that, you can use our board for face detection, object detection, as well as if you want to merge or merge different image merging and all, you can use our processor. So hope this one is clear. now it is a Q&A session. So any clarification or anything you want to ask from your side, you can do. Hope it was clear for you.
Any questions from the participants? Thank you, Sharon ma'am, for the session. The session gave us a good opportunity to understand more about C-DAC, its initiatives and important contributions. I extend our sincere, heartfelt gratitude for the valuable presence and insightful address. Thank you, ma'am.
Thank you. Thank you all for attending. If any doubt is there, you can definitely contact at any time. From our side, we will be giving full support for the development. In-person support is also there. So you can utilize that one and use our India's first indigenous microprocessor for our upcoming applications. Thank you. Thank you all.
Before we conclude, we would like to know your experience about the program. Would anyone like to share the feedback? We thank all participants for the active participation and the cooperation throughout the FDP. Thank you all. And please don't forget to fill the feedback on the ATAL portal. This is mandatory for eligibility to appear for the examination. The exam will be enabled at the ATA portal at 8 o'clock and duration will be 45 minutes. So kindly make sure to attend on time. Thank you.
ആടാ പറ. കേട്ടില്ല. അത് അയച്ചിട്ടുണ്ടല്ലോ, ആദ്യം തന്നെ അയച്ചിട്ടുണ്ട്. എവിടെ, ഗ്രൂപ്പിലാണോ? ഒരു സെക്കൻഡ്. എപ്പടാ ഞാനൊരു കാര്യം ചെയ്യാം, എല്ലാം കൂടി ഒരുമിച്ച് പറഞ്ഞടാ. മറ്റേ ഞാൻ അവസാനം എങ്ങനെ ചെയ്യാറ്? അങ്ങനെ തന്നെ ഞാൻ ചെയ്യാറുണ്ട്. സെക്ഷൻ 2 അവസാനം എന്തായേ? കുഴപ്പമില്ല, 3 നിരത്തിയിട്ടുണ്ട്. ആഘോഷിയുടെ അവര് അറ്റൻഡൻസ് ക്ലോസ് ചെയ്യട്ടെ. ഞാനവിടെ ഒപ്പിടാൻ ലേറ്റ് ആയി. ആ പട്ടിയച്ഛൻ നേരത്തെ വന്നില്ല. അല്ല, ഒപ്പിടാനായിട്ട് പോയത്, പക്ഷെ അച്ഛൻ നേരത്തെ എത്തണ്ടേ. ആളാ മീറ്റിംഗ് റൂമിൽ ഇറങ്ങി വരാണ്ട്. അയ്യോ, PDF അല്ലേ.